Scientists just broke a record that could change how we see the universe forever. Using the Chinese quantum satellite, known as Micius, they managed to link particles photons of light across a mind-boggling distance of over 1,200 kilometers. These particles became entangled, a strange and wonderful quantum state where they influence each other instantly, even though they were separated by a vast expanse of space. This is not just a cool experiment. It is a profound glimpse into how the very fabric of the universe might be woven together by invisible, instantaneous quantum threads. Albert Einstein, one of the greatest minds in history, could never accept this idea. He famously called entanglement spooky action at a distance, dismissing it as an impossibility, a sign that our understanding of quantum mechanics must be incomplete. But this groundbreaking experiment, and many others like it, have proven that the spookiness is real. Entanglement works exactly as the bizarre, counterintuitive rules of quantum physics predict. Imagine pulling a string on Earth and instantly feeling a tug on Mars, with no delay, no signal traveling between the two. That is the essence of quantum entanglement, a phenomenon so strange that it challenges our most deeply held intuitions about space, about time, and about the nature of reality itself. But why does this matter for something as grand as space exploration? The immediate, practical implications are revolutionary. This discovery could be the key to creating unhackable quantum communication systems. Imagine being able to send a perfectly secure message from Earth to a future colony on Mars, or to a distant spacecraft exploring the outer solar system, with the knowledge that any attempt to eavesdrop would be instantly detected. This is not science fiction. It is the promise of a quantum internet, a new kind of communication network built on the strange and wonderful rules of entanglement. But on a deeper, more philosophical level, this experiment hints at something even more profound. It suggests that the space between the stars may not be as empty as it seems. There could be a hidden layer of reality, a web of quantum connections that stretches across the entire universe, linking distant galaxies, stars, and perhaps even living beings, in ways we are only just beginning to understand. It is a vision of a cosmos that is not a collection of separate, isolated objects, but a single, vast, and deeply interconnected quantum system. At its heart, quantum mechanics is the science of the very small, the theory that describes how the fundamental building blocks of our universe, the electrons, the photons, the quarks behave, and their behavior is nothing like the predictable, clockwork world of our everyday experience. Unlike the solid, definite objects of classical physics, quantum particles are creatures of probability and potential. They can exist in multiple states at once, a phenomenon known as superposition. They can make seemingly random decisions about their properties only when they are observed. And, as we have seen, they can be linked together through entanglement, their fates intertwined across vast, cosmic distances. This quantum strangeness is not just a laboratory curiosity. It is the very engine that drives the cosmos. The stars in our sky shine because of a quantum phenomenon called tunneling, a process that allows the nuclei of atoms in the sun's core to overcome their mutual repulsion and fuse together, releasing the immense energy that powers our world. Without quantum tunneling, there would be no sunlight, no energy, no life. The very atoms that make up our bodies are stable only because of the strange, probabilistic rules of the quantum world, which prevent electrons from spiraling into the nucleus. And now, scientists are beginning to explore how these same quantum principles might explain some of the greatest mysteries in all of cosmology. Could quantum entanglement be the key to understanding the bizarre, information-scrambling nature of black holes? Those enigmatic objects where space and time are warped beyond all recognition. Could the ghostly, non-local connections of the quantum world help us to finally unravel the secrets of dark matter, the invisible substance that makes up most of the universe's mass. And could quantum mechanics hold the answer to one of the most mind-bending ideas in all of science? The possibility that our entire three-dimensional universe is a kind of cosmic hologram, a projection of information from a lower-dimensional reality. The Mikias satellite experiment is just the beginning of this grand and exciting journey. With each new discovery, with each new successful test of the strange and beautiful rules of the quantum world. We are peeling back another layer of reality, revealing a universe that is more interconnected, more mysterious, and more wonderful than we ever dared to imagine. And who knows, the next great breakthrough might not just change how we see the cosmos. It might fundamentally redefine the nature of reality itself. In the strange and beautiful landscape of modern physics, black holes spawned as the ultimate enigma, a place where the two great pillars of our understanding, Einstein's general theory of relativity and the laws of quantum mechanics, collide in a storm of paradox and mystery. For decades, we have seen black holes as purely astrophysical objects, the collapsed remnants of massive stars, gravitational behemoths whose immense pull warps the very fabric of space-time. But a new and revolutionary picture is beginning to emerge, a picture that suggests that these cosmic monsters are not just objects in the quantum world, but are, in a very real sense, quantum objects themselves. A groundbreaking new study has proposed that some of the very first black holes, the primordial black holes that are thought to have formed in the turbulent, fiery moments following the Big Bang, may carry with them a unique quantum fingerprint. This theory suggests that these ancient black holes might exhibit properties that are influenced by quantum chromodynamics, QCD. The theory that describes the strong nuclear force, the force that binds quarks and gluons together inside protons and neutrons. This is a staggering idea. It implies that a black hole is not just a region of curved spacetime, but is deeply and intimately tied to the fundamental quantum fields that govern the smallest scales of reality. This is a vision of a black hole as a kind of cosmic atom, a macroscopic object whose properties are dictated by the bizarre and often counterintuitive rules of the subatomic world. This new quantum view of black holes is inextricably linked to one of the most profound and important ideas in all of theoretical physics: Hawking radiation. In the 1970s, the brilliant physicist Stephen Hawking, in a stunning intellectual achievement, showed that black holes are not completely black due to the constant jittery fluctuations of the quantum vacuum near a black hole's event horizon, the point of no return. Pairs of virtual particles are constantly being created. Occasionally, one of these particles will fall into the black hole, while its partner escapes into space, carrying away a tiny amount of the black hole's mass energy. This slow, steady leakage of energy, now known as Hawking radiation, means that black holes are not eternal prisons of matter and information. They slowly evaporate over immense, almost unimaginable timescales, eventually disappearing in a final, brilliant flash of radiation. Detecting this faint, thermal glow from a real astrophysical black hole remains a significant and perhaps insurmountable experimental challenge. But scientists have found a clever way to study this phenomenon in the laboratory. By creating analog black holes, systems that mimic the properties of an event horizon, they have been able to observe effects that are remarkably similar to Hawking radiation. One of the most promising of these approaches involves using Bose-Einstein condensates, an exotic state of matter where millions of ultra-cold atoms behave as a single, coherent quantum entity. By manipulating these condensates with lasers, physicists can create a region where sound waves, or phonons, can enter but cannot escape, a sonic event horizon. And they have observed the spontaneous emission of phonon pairs from this horizon. a sonic analog of Hawking radiation. While this is not a direct detection of the cosmic phenomenon, it is a powerful confirmation of the underlying theoretical principles, and it gives us confidence that Hawking's strange and beautiful idea is a real feature of our universe. Another, more direct way to search for the quantum origins of black holes is to look for their fossilized imprints in the oldest light of the universe, the cosmic microwave background, CMB. The theory of cosmic inflation, as we have seen, proposes that the universe underwent a period of hyper-accelerated expansion in its first moments. During this period, tiny primordial quantum fluctuations in the density of the early universe would have been stretched to astronomical scales. In regions where these fluctuations were particularly large, the density could have been high enough for the region to collapse directly into a primordial black hole, bypassing the stellar collapse pathway. These primordial black holes, if they exist, would be a direct relic of the quantum nature of the infant universe, and they would have left a subtle but potentially detectable signature in the cosmic microwave background. They would act as gravitational lenses, slightly distorting the path of the ancient light as it traveled towards us, creating specific, localized patterns of temperature and polarization in the CMB. The search for these primordial black hole signatures is one of the most exciting frontiers in observational cosmology, a quest to find the fossilized remnants of the universe's first and most quantum objects. This idea is further supported by another, more recent, cosmic puzzle. Our most powerful telescopes, like the James Webb Space Telescope, have been discovering a surprising number of supermassive black holes in the very early universe, in galaxies that are seen as they were just a few 100 million years after the Big Bang. According to our traditional theories of black hole growth, which involve the slow accretion of gas and the occasional merger with other black holes, there simply has not been enough time for these black holes to grow so large, so quickly. The existence of these ancient cosmic behemoths suggests that they may not have started as small stellar mass black holes. They may have started from much larger and primordial black holes, formed directly from the quantum fluctuations of the early universe, are the perfect candidates for these seeds. This is a beautiful and elegant idea. It suggests that the largest, most massive objects in the universe today may have their origins in the smallest, most fundamental quantum processes of the very beginning of time. It is a direct and powerful link between the quantum and the cosmos. The new and revolutionary field of gravitational wave astronomy is also providing a powerful new window into the quantum nature of black holes. The Laser Interferometer Gravitational Wave Observatory. LIGO and its international partners have now detected the faint, almost imperceptible ripples in spacetime from dozens of black hole mergers. These gravitational waves are a direct and beautiful confirmation of Einstein's theory of general relativity. But as scientists have begun to analyze the detailed shape of these waves, the ring-down signal as the two black holes settle into a single final object, they have found subtle hints, subtle echoes, that may not be explained by classical general relativity alone. These echoes could be a sign of quantum effects at the event horizon, a quantum fuzziness that is not present in the classical picture. They could be the result of quantum tunneling near the event horizon, or of the complex quantum gravitational interplay that occurs when two of these massive quantum objects merge. While these findings are still preliminary and highly debated, they represent one of our first tentative glimpses into the realm of quantum gravity, the long sought-after theory that will unite the two great pillars of modern physics. The theoretical study of the quantum vacuum itself also provides clues. The intense gravitational field near a black hole's event horizon is predicted to warp the quantum vacuum in a dramatic way, a phenomenon known as vacuum polarization. This can lead to the spontaneous creation of real particle-antiparticle pairs from the vacuum, a process that is related to, but distinct from, Hawking radiation. Experiments in our most powerful particle accelerators, which can create incredibly strong electromagnetic fields, have observed analogous effects, strengthening our confidence that these quantum vacuum effects are a real and important part of black hole physics. They suggest that a black hole is not a passive, dead object, but is in a constant dynamic dialogue with the quantum vacuum that surrounds it, a dialogue that shapes its properties and its evolution. Another remarkable insight has emerged from the study of gamma-ray bursts, the most powerful and energetic explosions in the universe. These fleeting, brilliant flashes of high-energy radiation are often associated with the formation of a new black hole, either from the collapse of a massive star or the merger of two neutron stars. But some theoretical models suggest that they could also be the signature of the final explosive death of a primordial black hole as it evaporates completely through Hawking radiation. As a small primordial black hole reaches the end of its life, its temperature would skyrocket, and it would release its remaining mass in a final, brilliant burst of gamma rays. Observatories like NASA's Fermi Gamma Ray Space Telescope are constantly scanning the skies for such a distinctive final moment signal, a signal that would be a definitive confirmation of both the existence of primordial black holes and the reality of Hawking radiation. The deep connection between black holes and quantum information is perhaps the most profound and fruitful area of research in all of theoretical physics. The black hole information paradox, the apparent conflict between the prediction that information is lost in a black hole and the quantum principle that information can never be destroyed, has been a major driver of progress for decades. And the proposed solutions to this paradox have led to some of our most radical and revolutionary ideas about the nature of reality. The idea of black hole complementarity and the holographic principle suggest that the information is not lost, but is scrambled and encoded on the two-dimensional event horizon. And some have even proposed that the remnants of evaporated black holes, tiny, Planck-sized objects, could serve as a kind of cosmic memory bank, storing the quantum information of the matter that formed them. While these are highly speculative ideas, they are not without potential observational consequences. These quantum remnants, if they exist, would have a gravitational influence, and their presence could be inferred from their effect on the clustering of galaxies or through their subtle microlensing effect on the light from distant stars. And this brings us back to one of the greatest and most tantalizing mysteries of all, the nature of dark matter. Could the mysterious, invisible substance that makes up most of the universe's mass be nothing more than a vast population of primordial black holes? Forged in the quantum chaos of the early universe, the European Space Agency's Gaia mission, which is mapping the positions and motions of over 1 billion stars in our galaxy with unprecedented precision, could provide a definitive answer to this question. By looking for the telltale, microlensing signatures of these ancient quantum objects, Gaia may one day reveal that the dark gravitational scaffolding of our cosmos is a direct and beautiful legacy of the universe's quantum origins. The interplay between the quantum fluctuations of the early universe and the subsequent evolution of cosmic structures is a story that is still being written. But it is a story that is increasingly pointing towards a deep and profound unity. A unity where the smallest, most fundamental quantum processes are responsible for shaping the largest and most magnificent structures in the cosmos. The study of black holes as quantum objects is no longer a niche, theoretical pursuit. It is at the very heart of our quest to understand the universe, a quest that is revealing a cosmos that is more interconnected, more dynamic, and more wonderfully quantum than we ever imagined. In the quest to understand the universe's first fiery moments, Scientists have developed a powerful and innovative new tool, the simulation of quantum states on hyperbolic lattices. This cutting-edge approach, which combines the abstract beauty of non-Euclidean geometry with the computational power of modern physics, is allowing researchers to recreate the extreme and previously inaccessible conditions of the early universe in a controlled, virtual environment. This is a groundbreaking leap forward, a way to bridge the vast gap between the theoretical predictions of quantum physics and the observational data from our telescopes. At the heart of this new approach is the use of conformal field theories, CFTs, a special and highly symmetric class of quantum field theories that are thought to describe the behavior of matter at very high energies, like those present in the immediate aftermath of the Big Bang. And the natural geometric stage for these theories is not the familiar flat space of our everyday experience, but a negatively curved, hyperbolic space. By placing these CFTs on a discrete computational lattice that has the geometry of a hyperbolic plane, physicists can now perform precise and reliable simulations of the quantum dynamics of the infant cosmos. This is a remarkable achievement, a virtual time machine that allows us to explore the physics of the universe's birth. One of the most intriguing aspects of this research is its ability to shed new light on the process of cosmic inflation. As we have seen, inflation is the theory that the universe underwent a period of hyper-accelerated expansion in its first moments. This rapid stretching of spacetime would have taken the tiny, unavoidable quantum fluctuations of the primordial vacuum and amplified them to macroscopic and even astronomical scales. These amplified fluctuations then became the seeds of all the structure we see in the universe today. The galaxies, the clusters, the vast cosmic web. The hyperbolic lattice simulations are providing a new and powerful way to study this process in detail. They allow physicists to model the complex, quantum interplay between the inflating spacetime and the fluctuating quantum fields, and to calculate the precise statistical properties of the resulting density variations. These theoretical predictions can then be compared with the exquisitely precise measurements of the temperature fluctuations in the cosmic microwave background. The remarkable agreement between the predictions of these quantum simulations and the observational data is one of the strongest pieces of evidence we have that this strange and beautiful story of our quantum origins is, in fact, correct. The search for the echoes of these primordial quantum events is not limited to simulations. It is also a major focus of observational cosmology. The stretching of spacetime during inflation is predicted to have generated not just density fluctuations, but also primordial gravitational waves, ripples in the very fabric of spacetime itself. These gravitational waves are a unique and pristine messenger from the very beginning of time. They travel to us almost completely unimpeded from the moment of their creation, carrying with them a direct and unambiguous signature of the physics of inflation. Detecting these incredibly faint, ancient ripples is one of the holy grails of modern cosmology. And the search is on. Experiments like BICEP Keck at the South Pole and the upcoming Simons Observatory in the Atacama Desert are designed to search for a specific, swirling pattern of polarization in the cosmic microwave background, a B-mode polarization pattern that can only be produced by primordial gravitational waves. A definitive detection of these B-modes would be a Nobel Prize-worthy discovery, a direct confirmation of inflation, and a window into the physics of the universe at energies far beyond the reach of any terrestrial particle accelerator. Another, equally profound, quantum phenomenon that may have played a crucial role in the early universe is entanglement. Could the particles created in the fiery aftermath of the Big Bang have been born in a state of massive, cosmic-scale entanglement? And could this primordial entanglement have influenced the subsequent evolution of the universe? This is a fascinating and active area of research. Some have speculated that the strange, large-scale correlations that we see in the cosmic microwave background, the fact that the temperature fluctuations on opposite sides of the sky seem to be correlated in ways that defy a simple causal explanation, could be a sign of this primordial entanglement. Recent laboratory experiments have shown that entangled states can be surprisingly robust, capable of surviving in the kind of hot, dense, and chaotic environments that were present in the early universe. This lends a new plausibility to the idea that entanglement is not just a feature of our present-day quantum world, but was a key player in the cosmic drama from the very beginning. It suggests a universe that was born not as a collection of separate, independent particles, but as a single, holistic, and deeply entangled quantum state. The cosmic microwave background, that faint, ancient light that fills all of space, is our most powerful and precious tool for studying the quantum nature of the early universe. The tiny, 1 part in 100,000 temperature anisotropies in the CMB are a direct snapshot of the quantum fluctuations that existed when the universe was just 380,000 years old. By analyzing the precise statistical properties of these fluctuations, their size distribution, their correlations, their subtle deviations from perfect randomness, cosmologists can test the predictions of different models of inflation and can search for the telltale signs of new, exotic physics. Recent, increasingly precise maps of the CMB from missions like the Planck satellite have revealed subtle anomalies, features in the data that are not perfectly explained by our simplest models of inflation. There is a strange cold spot, a particularly large and cold region of the sky. There is a curious alignment of the largest scale patterns of fluctuation, a cosmic axis of evil, as it has been provocatively nicknamed. While these anomalies could just be statistical flukes, the result of looking at a single realization of a random process, they have also fueled speculation that they could be the signature of something deeper, something beyond our standard cosmological model. Could the cold spot be the aforementioned bruise from a collision with another bubble universe? Could the strange alignment be a sign of a more complex, anisotropic inflationary process, or even a relic of a pre-inflationary era? These are tantalizing, if highly speculative, possibilities. And they are driving a new wave of theoretical and observational research. The universe, it seems, is still full of surprises, and its oldest light may yet hold the key to its deepest secrets. The connection between the quantum and the cosmos is also being probed in our most powerful particle accelerators. By smashing particles together at incredibly high energies, experiments at the Large Hadron Collider are recreating, for a fleeting moment, the conditions of the early universe, a state known as a quark-gluon plasma. In this state, the protons and neutrons themselves melt, and their constituent quarks and gluons are free to move around in a hot, dense, and strongly interacting liquid. By studying the properties of this primordial plasma, physicists can learn about the nature of the strong nuclear force at the highest energies, and can test the predictions of quantum chromodynamics in an extreme regime that is otherwise inaccessible. These experiments are a form of cosmic archaeology, a way to study the fossilized remnants of the universe's first moments in a controlled, laboratory setting. The quantum mechanics of the Big Bang also brings us face to face with one of the most profound and challenging questions in all of science: what came before the Big Bang? The Standard Model, with its initial singularity, seems to suggest that this question is meaningless, but a new class of theories, rooted in a quantum description of gravity, is beginning to offer a different and perhaps more satisfying answer. Theories like loop quantum cosmology, an application of loop quantum gravity to the early universe, suggest that the Big Bang was not an absolute beginning, but a big bounce. In this scenario, our universe arose from the collapse of a previous contracting universe, as the contracting universe reached an incredibly high density. The quantum nature of space-time itself, its fundamental discreteness, would have created a powerful repulsive force, preventing the formation of a true singularity and causing the universe to bounce back into a new phase of expansion. In this picture, the universe is part of an eternal, cyclical process, with no absolute beginning or end. While we have no direct experimental evidence for this scenario yet, it is a mathematically consistent and conceptually beautiful idea. And it is an idea that could, in principle, be tested. The bounce would have left a specific and potentially detectable signature in the cosmic microwave background or in the spectrum of primordial gravitational waves. The search for these signatures is one of the most exciting and ambitious goals of future cosmological observations. The quest to understand the quantum mechanics of the early universe is a quest that is pushing the boundaries of our knowledge in every direction. It is a quest that connects the largest scales of the cosmos with the smallest, the most ancient light with the most advanced laboratory experiments, the most abstract theories with the most profound existential questions. It is a quest that is revealing a universe that was born from the subtle, beautiful, and endlessly creative dance of quantum probability. A universe whose deepest secrets are still waiting to be uncovered in the faint, ancient echoes of its own quantum beginning. The vast, dark, and seemingly empty spaces of our universe are not empty at all. They are filled with a mysterious, invisible substance, a dark matter that does not emit, absorb, or reflect light. And yet its gravitational influence is the dominant force that shapes the cosmos. It is the invisible scaffolding upon which the luminous structures of the universe, the stars, the galaxies, the great cosmic web are built. The existence of dark matter is not a speculation. It is a conclusion that is forced upon us by a wealth of independent astronomical observations. We see its effects in the rapid rotation of galaxies, where the outer stars are moving far too fast to be held in orbit by the visible matter alone. We see it in the gravitational lensing of distant light, where the gravity of massive galaxy clusters bends and distorts the images of background objects far more than their visible mass could account for. And we see it in the large-scale structure of the universe itself, the intricate, web-like pattern of filaments and voids, which our computer simulations tell us could not have formed without the gravitational influence of a vast, unseen component of matter. And yet, despite the overwhelming evidence for its existence, the nature of dark matter remains one of the greatest unsolved mysteries in all of science. We know it is there. We know it has gravity. But we have no idea what it is. This is a profound and humbling state of affairs. It means that 85% of the matter in our universe is made of a substance that is completely unknown to us. A substance that is not part of our otherwise incredibly successful standard model of particle physics. The quest to identify the dark matter particle is one of the most urgent and exciting challenges in modern science. A quest that is being pursued on multiple fronts, from the deepest underground laboratories to the most powerful particle accelerators and the most sensitive space telescopes. And it is a quest where the tools and concepts of quantum mechanics are playing an increasingly central role. One of the most promising avenues in the search for dark matter is the use of exquisitely sensitive, quantum-based detectors. The leading candidates for dark matter particles are weakly interacting massive particles. WIMPs, hypothetical particles that would have been produced in the hot, dense early universe and would interact with normal matter only through the weak nuclear force and gravity. These interactions would be incredibly rare, which is why dark matter is so difficult to detect. But they are not impossible. In deep underground laboratories, shielded from the constant bombardment of cosmic rays, physicists have built large detectors, filled with materials like liquid xenon or germanium crystals, in the hope of catching the faint, fleeting signal of a WIMP bouncing off an atomic nucleus, The challenge is immense. The expected signal is a tiny, almost imperceptible recoil of a single nucleus, an event that is easily drowned out by the background noise from natural radioactivity. This is where quantum technology comes in. A recent groundbreaking experiment at Fermilab and the University of Chicago has demonstrated a new and incredibly sensitive technique that uses the tools of quantum computing to search for a different kind of dark matter candidate, the axion. Axions are hypothetical, ultralight particles that were originally proposed to solve a different puzzle in particle physics, but which have also emerged as a compelling dark matter candidate. In the presence of a strong magnetic field, an axion could, very rarely, convert into a photon of a specific frequency. The experiment uses a superconducting qubit, the building block of a quantum computer, placed inside a cryogenically cooled microwave cavity. The qubit acts as an incredibly sensitive quantum antenna, capable of detecting the faint, single-photon signal that would be the telltale sign of an axion conversion. By carefully scanning through different frequencies, this quantum sensor can search for the elusive dark matter particle with a precision that was previously unattainable. This is a beautiful example of how the cutting-edge technologies developed for quantum computing are being repurposed to tackle some of the deepest and most fundamental questions in all of cosmology. Other related experiments, known as axion haloscopes, use large, powerful magnets and resonant cavities to try and amplify this faint action-to-photon conversion signal. And the search is also being pursued with quantum interferometers, devices that use the wave-like nature of light or matter to measure tiny disturbances with incredible precision. A passing dark matter particle could, in theory, cause a tiny, fleeting distortion in space-time, or a subtle change in the fundamental constants of nature, which could be detected as a phase shift in an interferometer. These are all incredibly challenging, and often needle in a haystack experiments. But they represent our best hope for finally, directly, detecting the dark matter particle and beginning to unravel its secrets. Another and equally important part of the dark matter puzzle is the search for its production in our most powerful particle accelerators. If dark matter is made of WIMPs or other new particles, then it should be possible to create them in the high-energy collisions at the Large Hadron Collider. The problem is that these dark matter particles, by their very nature, would be invisible to the detectors. They would not leave a track. They would not deposit any energy. So, how can we hope to see them? The answer is to look for what is not there. The signature of dark matter production at the LHC would be missing energy. When two protons collide, we can measure the energy and momentum of all the visible particles that fly out. If the total energy and momentum of these outgoing particles does not balance the initial energy and momentum of the colliding protons, it is a sign that some invisible particles have been produced and have escaped the detector unseen. This missing energy signature is a powerful tool in the search for new physics, and it has been used to search for a wide range of dark matter candidates, from the superpartners of supersymmetry to the Kaluza-Klein particles of extra-dimensional theories. So far, no definitive, unambiguous signal of dark matter production has been seen at the LHC. This has led some to question the WIMP paradigm and to explore other, more exotic possibilities. One of these is the idea of a hidden sector or a dark sector, a whole new family of particles and forces that interact very weakly, or not at all, with our familiar, standard model particles. Dark matter could be the lightest, stable particle in this hidden sector, and there could be portal interactions, new, very weak forces that connect our world with this dark world. The LHC is searching for the signs of these portals, for the rare events where a collision produces a particle, like a dark photon, that can then decay into the hidden sector. The search for dark matter is a beautiful and compelling example of the deep and powerful interplay between the very small and the very large. The fate of galaxies and the structure of the cosmos are determined by the properties of a particle that is so small, so weakly interacting, that it has, so far, completely eluded our most sensitive detectors. The quest to find it is a quest that is pushing the boundaries of our technology, of our theories, and of our very understanding of the quantum world. The mystery of dark matter is not just about identifying a new particle. It is about understanding a whole new sector of reality, a sector that may be as rich and as complex as the one we are familiar with. And the quantum nature of this dark world could have profound and unexpected implications for the cosmos. One of the most intriguing possibilities is that dark matter is not a single, simple particle, but has its own complex interactions, its own dark chemistry. Some anomalies in astronomical observations, like the surprisingly low density of dark matter in the cores of some dwarf galaxies, could be explained if dark matter particles can interact with each other through a new dark force. This self-interacting dark matter model is one that is being actively explored, both theoretically and observationally. The quantum nature of dark matter could also play a role in the formation of the very first structures in the universe. In the standard cold dark matter model, the dark matter particles are slow-moving and clumped together under gravity to form small, dense halos. These halos then act as the gravitational seeds for the formation of the first stars and galaxies. But if dark matter has different quantum properties, if it is fuzzy or wave-like, for example, then this process of structure formation could be very different. Fuzzy dark matter models, where the dark matter is made of incredibly light, bosonic particles that form a giant, galaxy-sized Bose-Einstein condensate, predict that the formation of very small, dwarf galaxies should be suppressed. A prediction that could be tested with future, ultra-deep astronomical surveys. Another, even more radical idea is that dark matter could be a window into the multiverse. In some brain world models, as we have seen, our universe is a three-dimensional membrane floating in a higher dimensional space. In this picture, dark matter could be the gravitational influence of ordinary matter that is confined to a nearby parallel brane. We cannot see the matter on the other brane, but we can feel its gravity, which leaks into our dimension. This is a beautiful and speculative idea, but it is one that makes certain testable predictions about the distribution and behavior of dark matter that could be searched for in future, high-precision astronomical observations. The quest to understand dark matter is a quest that is leading us into some of the deepest and most mysterious corners of the quantum world. It is a quest that is forcing us to be more creative, more imaginative, and more open-minded in our thinking about the fundamental nature of reality. Whether dark matter turns out to be a WIMP, an axion, a primordial black hole, or something even stranger and more unexpected, its discovery will undoubtedly trigger a revolution in our understanding of the cosmos. A revolution that will reveal a universe that is not just darker, but also far richer and more wonderfully quantum than we ever imagined. The strange, ghostly, and deeply interconnected world of quantum mechanics finds its ultimate expression in the intense, extreme, and often violent environments of the cosmos. The universe is a natural, and often spectacular, laboratory for testing the limits of our quantum theories, a place where the subtle, microscopic rules of the quantum realm are writ large on a celestial scale. The study of pulsars, the rapidly spinning, highly magnetized neutron stars that are the collapsed remnants of massive supernovae, is a prime example of this beautiful synergy between the quantum and the cosmic. And the hypothetical action particle, one of our leading candidates for dark matter, may be the key that unlocks a new and deeper understanding of these exotic quantum objects, actions, if they exist, are predicted to have a very specific and very weak interaction with photons in the presence of a strong magnetic field. The incredibly intense magnetic fields of a pulsar, which can be 1,000,000,000,000 times stronger than the Earth's, provide the perfect environment for this interaction to occur. A cloud of actions accumulating in the magnetosphere of a pulsar could be converted into a cloud of radiophotons, producing a specific, narrow, and potentially detectable line in the pulsar's radio spectrum. The search for this action line is a new and exciting frontier in radio astronomy, a way to use the universe's own natural particle accelerators to search for one of its most elusive and mysterious components. But pulsars are not just potential action detectors, they are, in their very essence, quantum objects. A neutron star is a star that has collapsed to such an incredible density that its atoms have been crushed out of existence. It is a giant, city-sized atomic nucleus, composed mostly of neutrons, packed together so tightly that their behavior is governed not by classical physics, but by the strange and beautiful rules of the quantum world. One of the most remarkable of these is the phenomenon of superfluidity at the incredibly high densities and relatively low temperatures inside a neutron star. The neutrons are predicted to form a superfluid, a quantum state of matter that flows with absolutely no viscosity, no friction. And the protons within the star are predicted to form a superconductor, a state that conducts electricity with zero resistance. This is not just a theoretical curiosity. The existence of this quantum superfluid in the interior of neutron stars is thought to be the explanation for one of their most mysterious and long-observed behaviors. Glitches. A pulsar, because it is constantly radiating away energy, should be spinning down at a slow, steady, and predictable rate. But occasionally, astronomers observe a sudden, abrupt increase in a pulsar's spin rate, a glitch. The leading explanation for these glitches is that they are a result of the interaction between the solid outer crust of the neutron star and the rapidly spinning superfluid interior. The superfluid, because it has no viscosity, can spin at a different rate from the crust. But occasionally, the two can become momentarily coupled, transferring a burst of angular momentum from the superfluid to the crust and causing the star to suddenly spin up. The study of these pulsar glitches is a remarkable and powerful way to probe the strange, quantum state of matter that exists in the heart of a neutron star, a state that is impossible to replicate in any terrestrial laboratory. The universe as a laboratory for quantum mechanics is a theme that extends far beyond the realm of pulsars and axions. The distant, brilliant beacons of quasars, the intensely luminous centers of young, active galaxies, powered by supermassive black holes, have recently been used to perform one of the most profound and beautiful tests of the fundamental principles of quantum mechanics itself. As we have seen, the phenomenon of quantum entanglement, the spooky action at a distance, is one of the most bizarre and counterintuitive predictions of the theory. The Bell test experiments, which have confirmed this non-local connection with incredible precision, rely on a source of true, unpredictable randomness to set the measurement directions for the two entangled particles. This is to close a potential loophole, the freedom of choice loophole, which posits that the particles and the measurement devices could have been secretly correlated in the past by some unknown, local hidden variable. To close this loophole as definitively as possible, a recent groundbreaking experiment used the light from two very distant quasars located on opposite sides of the sky to set the measurement choices. The light from these quasars has been traveling for billions of years, and it was created in two completely causally disconnected regions of the early universe. The random fluctuations in the color of this ancient light were used to trigger the measurement settings in the experiment, ensuring that there was no possible way for the entangled particles to have known in advance what they were going to be asked. The experiment, once again, confirmed the predictions of quantum mechanics with stunning accuracy, ruling out any possibility of a local, realistic explanation for entanglement. It is a beautiful and profound demonstration of how the vastness of the cosmos can be used as a tool to probe the deepest secrets of the quantum world, and how the light from the universe's dawn can be used to confirm the strange and wonderful nature of our present reality. The deep and intimate connection between the quantum world and the cosmos is a two-way street, just as the universe can be used as a laboratory to test the principles of quantum mechanics. Quantum mechanics can be used as a tool to understand the origin and evolution of the universe itself. The phenomenon of quantum tunneling, the ability of a particle to pass through a classically forbidden energy barrier, is a prime example of this synergy. As we have seen, quantum tunneling is the engine that powers the stars. The protons in the sun's core do not have enough thermal energy to overcome their mutual electrostatic repulsion and fuse together. It is only by tunneling through this repulsive barrier that they can get close enough for the strong nuclear force to take over, initiating the process of thermonuclear fusion and releasing the energy that makes life on Earth possible. But the role of quantum tunneling extends far beyond the hearts of stars. A recent groundbreaking experiment, led by the researcher Robert Wild, has shown that quantum tunneling can also play a crucial role in the cold, sparse environment of interstellar space. By simulating the conditions of these vast molecular clouds in the laboratory, the team was able to show that quantum tunneling can enable chemical reactions to occur at temperatures near absolute zero, reactions that would be completely impossible according to classical chemistry. This is a profound discovery. It means that the complex organic molecules that are the building blocks of life may not just be formed in the warm, gentle environments of protoplanetary disks, but can also be synthesized in the coldest, darkest, and emptiest regions of the galaxy through the strange and wonderful magic of quantum tunneling. It suggests that the chemical precursors to life are far more widespread and are formed far more readily than we ever thought possible. From the fiery hearts of stars to the cold depths of interstellar space, the subtle and often counterintuitive rules of the quantum world are the silent, invisible architects that are shaping the cosmos, creating the conditions for complexity, for chemistry, and ultimately, for life itself. The universe, it seems, is a quantum phenomenon, through and through, the cosmic story of creation, from the first fiery moments of the Big Bang to the emergence of the rich and complex universe we see today, is a story that is fundamentally shaped by the principles of quantum mechanics. The very existence of matter, the stability of atoms, the light of the stars, all of these are a testament to the strange and beautiful rules that govern the subatomic world. And as our understanding of these quantum processes deepens, we are beginning to piece together a new and more profound picture of our own cosmic origins. The phenomenon of quantum tunneling, as we have seen, is not just a laboratory curiosity. It is a fundamental engine of cosmic evolution. It is what allows stars to shine, releasing the energy that powers life and forging the heavy elements that make up our bodies and our world. And it is a process that may be at work in the most extreme and mysterious environments in the universe. The intense gravitational fields near a black hole, for example, create a powerful energy barrier for particles trying to escape. But quantum tunneling could, in theory, allow particles to leak out, a process that is related to, but distinct from, Hawking radiation. This could have profound implications for our understanding of black hole thermodynamics and the ultimate fate of the information that falls into them. Similarly, the study of the dense, exotic matter in the heart of a neutron star is a study of quantum mechanics in its most extreme form. The immense pressure crushes matter into a state where quantum effects, like the Pauli exclusion principle and superfluidity become the dominant reality. Our observations of these strange quantum stars, through their regular clock-like pulses and their occasional sudden glitches, are providing a unique and powerful window into the behavior of matter at densities that are impossible to replicate on Earth. And what of the very beginning? The moment of the Big Bang itself is the ultimate quantum event, a moment where the entire universe was compressed into a state of unimaginable energy and density, a state where the laws of classical physics break down completely. To understand this moment, we need a theory of quantum gravity, a theory that can describe the quantum nature of space-time itself. And while we do not yet have a complete theory, the clues are beginning to emerge. The study of the cosmic microwave background, the faint afterglow of the Big Bang, has revealed a pattern of tiny primordial fluctuations that are the fossilized remnants of the quantum fluctuations of the early universe. These fluctuations, stretched to astronomical scales by the process of cosmic inflation, are the seeds from which all the galaxies and large-scale structures in the universe grew. We are, in the most literal sense, the macroscopic manifestation of microscopic quantum randomness. The journey to understand the quantum cosmos is a journey that is still in its infancy, but it is a journey that is already revealing a universe that is far stranger, more interconnected, and more wonderfully creative than our classical intuition could ever have imagined. The discoveries of tunneling, of fusion, of superfluidity, of primordial fluctuations are all just stepping stones on a path towards a deeper and more unified understanding of reality. And as our tools, both theoretical and experimental, become more powerful, we are poised to uncover even more profound and beautiful secrets. Future observations of primordial gravitational waves could give us a direct glimpse into the physics of inflation. The moment when the quantum became the cosmic, the direct detection of Hawking radiation from a black hole would be a stunning confirmation of the deep connection between gravity, thermodynamics, and the quantum vacuum. And the development of a complete theory of quantum gravity would be the ultimate triumph of the human intellect. A single, elegant theory that could describe the entire universe, from the smallest quantum fluctuation to the largest cosmic structure, within a single, coherent framework. But this quest is not just about finding answers. It is also about asking better questions. How does the strange, non-local nature of quantum entanglement play out on a cosmic scale? What is the role of the observer, of consciousness? In a universe that seems to be fundamentally probabilistic, is our universe just one of many in a vast quantum multiverse? These are questions that may not have simple answers, questions that may push the very limits of what science is capable of addressing. But they are questions that we are now, for the first time in human history, equipped to ask in a rigorous, scientific way. The study of the quantum cosmos is not just about understanding the universe out there, it is also about understanding ourselves. We are quantum beings, living in a quantum universe. The atoms that make up our bodies, the light that allows us to see, the very thoughts that flicker through our minds, all of these are governed by the same strange and beautiful rules of the quantum world. To study the quantum cosmos is to study the very fabric of our own existence. And as we continue on this journey, as we peer deeper into the mysteries of the quantum realm, we are not just unraveling the secrets of the universe, we are also, in a very real sense, unraveling the secrets of ourselves. The accelerating expansion of the universe, driven by the mysterious force of dark energy, is one of the most profound and challenging discoveries in the history of science. And the quantum world, with its seething, energetic vacuum, may hold the key to understanding this cosmic mystery. The incessant, jittery fluctuations of the quantum fields that permeate all of space give rise to a zero-point energy, an irreducible minimum energy of the void, and this vacuum energy, according to our current understanding, should have a powerful gravitational effect. It should act as a cosmological constant, a form of energy with a strong negative pressure that would cause the very fabric of spacetime to expand at an accelerating rate. This is a beautiful and elegant connection. It suggests that the grand cosmic drama of the universe's expansion is being driven by the subtle, microscopic dance of quantum mechanics. But this beautiful picture is marred by the vacuum catastrophe, the colossal discrepancy between the theoretical calculation of the vacuum energy and its observed value. This has led many physicists to explore alternative possibilities. Perhaps dark energy is not the energy of the vacuum, but is a new, dynamic quantum field, a quintessence that is slowly evolving over cosmic time. Or perhaps our understanding of gravity itself is incomplete, and the accelerated expansion is a sign of new physics beyond Einstein's general relativity. But another, even more profound, possibility has emerged from these investigations. The quantum fluctuations of the early universe, the very same fluctuations that are thought to have seeded the formation of galaxies, may have also played a direct role in shaping the properties of dark energy itself. Some theories suggest that the value of the cosmological constant is not a fixed, fundamental parameter of nature, but is a dynamical variable, a value that was set by the specific, random outcome of quantum fluctuations during the inflationary epoch. In this view, our universe is just one of a vast cosmic multiverse of possibilities, and we just happen to live in a universe where the quantum dice roll of inflation resulted in a small, positive value for the dark energy, a value that is conducive to the formation of structure and life. This is a deeply unsettling, but also deeply compelling idea. It suggests that the ultimate fate of our universe, its destiny to expand forever into a cold, dark, and empty void, may be the result of a single, random quantum event that occurred in the first fraction of a second of its existence. The study of the early universe, through the lens of quantum mechanics, is a journey into the very heart of creation. It is a quest to understand how, from a state of almost perfect simplicity and uniformity, the rich, complex, and beautiful tapestry of the cosmos was woven. The inflationary period, that brief, but spectacular, moment of hyper-accelerated expansion, is the key to this story. It is the bridge between the quantum and the cosmic, the mechanism that took the microscopic, probabilistic weirdness of the quantum world and stretched it to astronomical scales. The density variations that gave rise to galaxies, the primordial gravitational waves that may one day tell us about the physics of the very beginning, the very properties of the dark energy that is shaping our future. All of these may be the fossilized relics of the quantum fluctuations of the inflationary vacuum. The cosmic microwave background is our most precious and powerful window into this primordial quantum era. The tiny 1 part in 100,000 temperature fluctuations in the CMB are a direct photographic image of the state of the universe when it was just a few 100,000 years old. And by studying the precise statistical properties of these fluctuations, we can test the predictions of our quantum cosmological models with incredible precision. And these tests have been, so far, stunningly successful. The observed pattern of fluctuations is a near-perfect match for the predictions of the simplest models of inflation, a powerful confirmation of the idea that the grand architecture of our cosmos has its roots in the inherent and beautiful uncertainty of the quantum world. But the study of the CMB is also revealing subtle hints of new and even stranger physics. The anomalies we have discussed, the cold spot, the cosmic axis of evil, may be statistical flukes, but they may also be the first faint whispers of a reality that is even more complex and more wonderfully quantum than we have yet imagined. They may be the signs of a more complex inflationary history, of a pre-inflationary era, or even of a connection to a larger cosmic multiverse. The universe, it seems, is still full of quantum secrets, and its oldest light is our best hope for uncovering them. The connection between the quantum and the cosmic is not just about the early universe. It is also about the here and now. The strange, non-local reality of quantum entanglement, the spooky action at a distance, is a phenomenon that is now being tested on a cosmic scale. As we have seen, the use of distant quasars to set the measurement choices in a Bell test experiment has provided our most definitive refutation yet of Einstein's local realism. It is a beautiful demonstration of how the vastness of the cosmos can be used as a tool to probe the deepest and most counterintuitive aspects of the quantum world. But what if this connection goes even deeper? What if the universe itself, at the very largest scales, is a single, vast, and deeply entangled quantum system? This is a mind-bending idea, but it is one that is being taken seriously by some of the most creative thinkers in modern physics. The strange, large-scale correlations that we see in the cosmic microwave background, the fact that the temperature fluctuations on opposite sides of the sky seem to be more correlated than they should be, could be a sign of a primordial, cosmic-scale entanglement, a non-local connection that was established in the very first moments of the universe's existence and has persisted to this day. If this is true, it would mean that our universe is not a collection of separate, causally disconnected regions, but is a single, holistic, and deeply non-local quantum entity. It would be the ultimate confirmation of the quantum worldview, a vision of a universe that is profoundly and beautifully. 1. The study of top quarks and other heavy, unstable particles at the Large Hadron Collider is also providing a new and powerful window into the interplay between the quantum world and the extreme environments of the cosmos. The discovery that entanglement can persist, even for a fleeting moment, in these high-energy, chaotic collisions is a testament to the robustness of this strange quantum connection. And it is providing crucial insights into the physics of the early universe, of black holes, of the exotic states of matter that may exist in the hearts of neutron stars. By recreating these extreme cosmic conditions in the laboratory, we are learning about the fundamental quantum rules that govern the universe in its most violent and most mysterious regimes. The journey to understand the quantum cosmos is a journey that is still very much in progress. But it is a journey that has already transformed our understanding of the universe and our place within it. It has shown us a universe that is born from the creative uncertainty of the quantum void, a universe whose grandest structures are the macroscopic fossils of microscopic quantum fluctuations, a universe that is bound together by the invisible, instantaneous threads of quantum entanglement. And it has revealed a deep and profound unity between the very small and the very large, between the laws that govern the subatomic world and the laws that shape the destiny of the cosmos itself. The next generation of experiments, the more precise maps of the cosmic microwave background, the more sensitive gravitational wave detectors, the more powerful particle accelerators will undoubtedly reveal even more profound and beautiful secrets. They may confirm the existence of primordial gravitational waves, providing a direct glimpse into the moment of inflation. They may unravel the mystery of dark matter, revealing a whole new, hidden sector of the quantum world. They may even provide the first tantalizing hints of a final, unified theory of quantum gravity. But whatever these future discoveries may be, one thing is certain: they will only deepen our appreciation for the strange, beautiful, and endlessly fascinating quantum nature of our cosmic home. They will remind us once again that the universe is not just stranger than we imagine, but stranger than we can imagine. The quest to understand the universe, in all its vastness and complexity, is a journey that inevitably leads us to the most extreme, the most exotic, and the most mysterious objects in the cosmos. And at the very heart of this journey lies the study of black holes and neutron stars. The ultra-dense, collapsed remnants of massive stars, celestial objects that are not just laboratories for extreme physics, but are, in their very essence, macroscopic quantum phenomena. The recent groundbreaking experiment that used hyperbolic lattices to simulate the quantum states of the early universe is a powerful example of this new and exciting frontier. By creating an artificial computational spacetime with the geometry of a hyperbolic plane, physicists are now able to model the behavior of quantum fields in the kind of curved, dynamic environments that are thought to have existed in the immediate aftermath of the Big Bang, or in the immediate vicinity of a black hole. This is a revolutionary new tool. It allows us to explore the complex and often counterintuitive interplay between quantum mechanics and general relativity in a controlled, virtual environment, providing new insights into some of the deepest and most long-standing puzzles in all of science. One of these puzzles is the nature of the strong nuclear force at the highest energies. The theory of quantum chromodynamics QCD describes this force with incredible precision, but its equations become incredibly difficult to solve in the extreme. High-density environments of a neutron star core or a quark-gluon plasma. The hyperbolic lattice simulations are providing a new and powerful way to tackle these calculations, shedding new light on the exotic states of matter that are thought to exist in these extreme, cosmic crucibles. The core of a neutron star, for example, is a place of almost unimaginable density, a place where matter is crushed to a state that is billions of times denser than anything we can create on Earth. In this environment, the neutrons themselves are predicted to dissolve into a sea of their constituent quarks and gluons, a state of matter known as quark matter. And the quarks themselves may form a color superconductor, a strange quantum state where they flow with zero resistance. The study of these exotic states of matter is not just a theoretical exercise. It has real, observable consequences. The precise properties of the matter in a neutron star's core determine its maximum mass, its cooling rate, and its behavior during the violent merger with another neutron star. The gravitational waves and the electromagnetic signals that we detect from these mergers are a direct probe of the quantum physics of extreme density, a way to test our theories of QCD and exotic matter in a way that is impossible in any terrestrial laboratory. The quantum nature of these extreme astrophysical objects is not just about the state of their matter, it is also about the very fabric of space-time itself. The black hole information paradox, as we have seen, is a deep and profound conflict between the principles of quantum mechanics and general relativity, and its resolution is thought to lie in a deeper quantum understanding of the black hole's event horizon. The hyperbolic lattice simulations and other related theoretical tools are allowing physicists to explore the quantum geometry of the event horizon in unprecedented detail. They are studying how quantum information is scrambled and encoded on the horizon, and how it might be subtly imprinted on the outgoing Hawking radiation. This is a quest that is leading to some of the most radical and revolutionary ideas in modern physics, including the Reshaping conjecture and the holographic principle, ideas that suggest that space-time itself may be an emergent. Quantum informational phenomenon. The study of Bose-Einstein condensates, BECs, another exotic quantum state of matter, is also providing a powerful new window into these mysteries. A BECE is a state where a large number of bosonic particles, cooled to temperatures near absolute zero, all collapse into the same single quantum state, behaving as a single, coherent, macroscopic quantum object. These systems are a kind of quantum simulator, a controllable laboratory system that can be used to model the behavior of other, more complex and inaccessible quantum systems. A recent experiment conducted aboard the International Space Station has created the coldest and most stable BECCs ever produced. And in the microgravity environment of space, these quantum clouds can be studied for much longer periods of time, allowing for incredibly precise measurements of their quantum properties. Scientists are now using these space-based BECs to simulate a wide range of astrophysical and cosmological phenomena, from the dynamics of dark energy to the quantum nature of black holes. One of the most exciting possibilities is the creation of a graviton condensate. Gravitons, the hypothetical quantum particles of gravity, are bosons, and so, in principle, they could form a Bose-Einstein condensate. Some have speculated that a black hole could be, in its very essence, a condensate of a vast number of gravitons, a single, macroscopic quantum object held together by its own collective gravity. While this is a highly speculative idea, the ability to study the properties of BECs in the laboratory, and now in space, is providing a new and powerful set of tools for exploring these profound and beautiful ideas. The quantum world, it seems, is everywhere. It is in the fiery hearts of stars, in the cold depths of interstellar space, in the dense, exotic matter of neutron stars, and in the enigmatic, information-scrambling horizons of black holes. And the study of these cosmic quantum laboratories is revealing a universe that is far more interconnected, more dynamic, and more wonderfully strange than we ever imagined. The phenomenon of superfluidity, the ability of a quantum fluid to flow with zero viscosity, is another beautiful example of this cosmic quantum connection. We have already seen how the superfluidity of neutrons is thought to be responsible for the glitches in the rotation of pulsars. But superfluidity may also play a role in the very formation of these objects. The collapse of a massive star in a supernova explosion is an incredibly complex and violent event. And recent sophisticated computer simulations have shown that the superfluid nature of the nascent neutron star's core could have a dramatic effect on the dynamics of the explosion itself, influencing the way that neutrinos are trapped and released, and potentially playing a key role in powering the explosion. The study of neutrinos themselves, the ghostly, weakly interacting particles that are produced in vast numbers in the Sun and in supernovae, is another frontier where the quantum and the cosmic meet. The discovery that neutrinos have a tiny but non-zero mass, and that they can oscillate or transform from one flavor to another as they travel, was a major breakthrough in particle physics and a clear sign of physics beyond our standard model. And the universe itself is our most powerful neutrino detector. The IceCube Neutrino Observatory at the South Pole uses a cubic kilometer of the Antarctic ice as a giant natural detector, searching for the faint flashes of light produced when a high-energy neutrino from a distant astrophysical source interacts with an atom in the ice. These high-energy neutrinos are a unique and powerful messenger, a way to probe the most violent and energetic process in the universe. From the hearts of active galactic nuclei to the mysterious sources of ultra-high energy cosmic rays. And their quantum properties, their oscillations and their interactions, are a key part of the story. The quantum world is not a separate, isolated realm of reality. It is the fundamental, underlying operating system of the entire cosmos. And as our ability to observe the universe and to simulate it becomes more and more sophisticated, we are beginning to see the deep and beautiful ways in which the subtle, strange, and often counterintuitive rules of the quantum realm are responsible for shaping the grand, magnificent, and awe-inspiring tapestry of the cosmos we inhabit. The journey to understand the quantum cosmos is a journey that is constantly pushing the boundaries of our technology and our imagination. And in the year 2024, a series of groundbreaking discoveries have brought the strange and beautiful world of quantum mechanics into sharper focus than ever before, revealing its profound influence on everything from the heaviest particles in the universe to the most extreme and exotic celestial objects. One of the most remarkable of these was the first definitive observation of quantum entanglement in top quarks, the most massive elementary particles ever discovered. This was an achievement of incredible technical virtuosity, conducted by the CMS collaboration at the Large Hadron Collider. Top quarks are incredibly unstable, decaying in a fraction of a yoctosecond, a time so short it is difficult to comprehend. The fact that the delicate, non-local connection of entanglement can be established and maintained, even for this fleeting instant, in the chaotic, high-energy environment of a proton-proton collision, is a stunning testament to the robustness of this fundamental quantum phenomenon. It pushes the verification of quantum mechanics into a new and previously unexplored regime of mass and energy, a regime that is closer to the conditions of the early universe than any we have been able to study before. This discovery is not just a confirmation of what we already knew. It opens up a new window into the quantum world. The top quark, because of its enormous mass, has a unique and very strong coupling to the Higgs field. By studying the entanglement of top quarks, physicists can probe the quantum nature of the Higgs field itself and can search for subtle deviations from the predictions of the standard model that could be a sign of new physics, of new particles or new forces that interact preferentially with the heaviest particles. Another, related breakthrough came from the study of entanglement in mesons, composite particles made of a quark and an antiquark. By studying the entangled decay products of these particles, physicists are gaining new insights into the subtle and still not fully understood violation of CP symmetry, the slight difference in the behavior of matter and antimatter that is thought to be responsible for the fact that our universe is made of matter at all. The ability to create and manipulate these entangled, heavy particle states is not just about testing fundamental physics, it is also about developing new quantum technologies. While photons are the current workhorse of quantum communication, heavy particles could, in principle, offer new and more robust ways to encode and transmit quantum information in certain specific contexts. The year 2024 has also been a landmark year for the study of exotic quantum states of matter on a cosmic scale. The observation of Bose-Einstein condensates aboard the International Space Station has provided a new and powerful laboratory for studying the collective quantum behavior of matter in a microgravity environment. These experiments are not just about creating a new fifth state of matter. They are about using these highly controllable, macroscopic quantum objects to simulate other, more complex and inaccessible systems, from the superfluid core of a neutron star to the quantum nature of dark energy. This is the dawn of the era of quantum simulation, a new and powerful tool for exploring the universe. The study of neutron stars themselves has also seen remarkable progress. The detection of gravitational waves from the merger of two neutron stars has provided an unprecedented multi-messenger view of these extreme quantum objects. By combining the gravitational wave signal with the electromagnetic signals, the light, the gamma rays, the radio waves that are emitted in the aftermath of the collision, astronomers are able to piece together a detailed picture of what happens when two of these city-sized atomic nuclei smash into each other. This data is providing crucial, new constraints on the equation of state of nuclear matter, the relationship between the pressure and the density of matter at the most extreme conditions in the universe. It is helping us to understand whether the core of a neutron star is made of simple neutrons or of more exotic states, like a quark-gluon plasma or strange matter. These are questions that are at the very heart of nuclear and particle physics. and the universe itself is providing us with the ultimate laboratory for answering them. The connection between the quantum and the cosmic is also being explored in the search for dark matter. As we have seen, the use of quantum sensors, like superconducting qubits and interferometers, is revolutionizing the search for actions and other light-dark matter candidates. These experiments are a beautiful example of how the tools of one quantum revolution, the revolution in our ability to control and manipulate single quantum systems, are being used to fuel the next, the revolution in our understanding of the fundamental nature of the cosmos. The year's discoveries are a powerful reminder that the universe is a deeply quantum place. The strange and beautiful rules of the quantum world are not confined to the sterile, controlled environment of the laboratory. They are at work everywhere, from the fleeting, entangled dance of top quarks at the LHC to the superfluid heart of a distant neutron star. From the quantum foam of the early universe to the very fabric of space-time itself. And as our ability to observe, to simulate, and to understand these quantum phenomena continues to grow, we are not just adding new details to our picture of the universe. We are fundamentally transforming it, revealing a cosmos that is more interconnected, more dynamic, and more wonderfully, beautifully, and profoundly quantum than we ever imagined. The study of quantum spin, an intrinsic and deeply mysterious property of fundamental particles, has also seen a year of remarkable and illuminating discoveries, further blurring the line between the microscopic world of the quantum and the macroscopic world of the cosmos. Quantum spin is not a physical rotation in the classical sense. It is a fundamental quantum mechanical property, a form of intrinsic angular momentum that gives particles a kind of magnetic orientation. And the alignment and interaction of these tiny quantum spins can have profound and large-scale consequences. A recent groundbreaking observation has revealed peculiar and highly ordered spin alignments in the expanding remnants of a supernova explosion. This suggests that the violent, chaotic process of a star's death may be influenced, and perhaps even shaped, by the collective quantum behavior of the spins of its constituent particles. The core collapse of a massive star is an event of almost unimaginable complexity. As the star's core is crushed by gravity to the density of an atomic nucleus, the spins of the neutrons and protons play a crucial role. The Pauli exclusion principle, which forbids two identical fermions from occupying the same quantum state, creates a powerful degeneracy pressure that resists the collapse. And the alignment of the spins of the particles can give rise to a powerful macroscopic magnetic field. The discovery of these spin-aligned structures in a supernova remnant provides a new and powerful piece of evidence for the importance of these quantum effects in the dynamics of stellar explosions. It suggests that the shape and evolution of a supernova remnant may not just be determined by hydrodynamics and shock waves, but also by the subtle and previously unobservable quantum magnetism of the exploding star. This has a direct bearing on our understanding of neutron stars. The incredibly strong magnetic fields of pulsars and magnetars are one of their most defining and also most mysterious features. And the leading theory is that these fields are a relic of the spin-aligned quantum state of the matter in the progenitor star's core, a field that has been amplified to an incredible degree during the gravitational collapse. The new observations of spin alignment in supernova remnants provide a direct causal link in this story, connecting the quantum properties of the star before its death to the macroscopic astrophysical properties of the compact object it leaves behind. The role of quantum spin is not just limited to the death of stars, it is also a key player in their life. The magnetic fields of stars like our Sun, which are responsible for phenomena like solar flares and coronal mass ejections, are generated by a complex dynamo process in their interiors, a process that is driven by the interplay of convection, rotation, and the magnetic properties of the plasma. And at a fundamental level, these magnetic properties are determined by the quantum spin of the electrons and the atomic nuclei. By studying the polarization of the light from distant stars, a technique that is sensitive to the presence of magnetic fields, astronomers are now able to map the magnetic activity of other suns, providing new insights into the quantum dynamo processes that are at work in the hearts of stars. This is crucial for our understanding of space weather and the potential habitability of exoplanets. A planet orbiting a star with a very active and spin-driven magnetic cycle would be subject to a much more intense and variable flux of high-energy particles and radiation, which could have a profound impact on its atmosphere and its ability to support life. And what of dark matter? The nature of this mysterious, invisible substance is one of the greatest unsolved puzzles in all of science. But what if the key to its identity lies in its quantum spin? The different dark matter candidates that have been proposed, WIMPs, actions, sterile neutrinos, all have different and specific spin properties. A WIMP is predicted to be a fermion with spin 1/2. An action is a boson with spin 0. By designing experiments that are sensitive to the spin-dependent interactions of dark matter with normal matter, physicists are hoping to finally distinguish between these different possibilities. The search for dark matter is not just a search for a new particle, it is a search for a new kind of quantum spin, a new fundamental player in the cosmic spin dance. The influence of quantum spin may even extend to the very largest scales of the cosmos. In the very early universe, the primordial plasma of particles and antiparticles would have been a sea of quantum spins, and some have speculated that a primordial cosmic magnetic field could have created a slight overall alignment of these spins, a cosmic spin polarization. While this is a highly speculative idea, such a primordial spin alignment could have left a subtle and potentially detectable signature in the cosmic microwave background, or in the large-scale distribution of galaxies. The search for these faint cosmic scale signatures of quantum spin is a new and exciting frontier in observational cosmology. The study of quantum spin is a beautiful example of the profound and often surprising interconnectedness of the universe. A single, intrinsic, and deeply quantum property of a fundamental particle can have consequences that ripple outwards, shaping the life and death of stars, the habitability of planets, the nature of dark matter, and perhaps even the large-scale structure of the cosmos itself. It is a reminder that to understand the universe, we cannot just study its different parts in isolation. We must study it as a single, unified, and deeply interconnected quantum system. And as our ability to measure and to model the subtle effects of quantum science continues to improve, we are not just adding a new chapter to our physics textbooks. We are gaining a new and more profound appreciation for the intricate, beautiful, and spin-driven music of the cosmos. The universe is constantly bombarding us with messengers from the most extreme and violent corners of the cosmos. Ultra-high energy cosmic rays, particles that have been accelerated to energies far beyond anything we can achieve on Earth, are a powerful and enigmatic probe of the fundamental laws of nature and recent discoveries. From observatories like the Pierre Auger Observatory in Argentina and the IceCube Neutrino Observatory at the South Pole are revealing the deep and profound role that quantum mechanics plays in the story of these cosmic travelers. These cosmic rays are not just fast, they are relics of some of the most powerful and energetic astrophysical engines in the universe. The swirling, chaotic environments around supermassive black holes, the rapidly spinning, highly magnetized magnetospheres of pulsars, the expanding, turbulent shock waves of supernova remnants. The precise mechanisms by which particles are accelerated to these incredible, ultra-high energies are still not fully understood, but it is clear that quantum processes must be at play. In the intense magnetic fields of a pulsar, for example, quantum electrodynamic effects, like the creation of electron-positron pairs from the vacuum, are thought to play a crucial role in the acceleration process. In the relativistic jets that are launched from the vicinity of a black hole, quantum tunneling may allow particles to surf the shock waves, gaining energy with each pass. The study of these cosmic accelerators is a study of quantum mechanics in its most extreme and most violent form. As these cosmic rays travel across vast intergalactic distances to reach us, they interact with the quantum fields that fill all of space. Their journey is not a simple, straight-line path through an empty void. They interact with the photons of the cosmic microwave background, with the faint, diffuse magnetic fields that thread the cosmic web, and with the virtual particles of the quantum vacuum itself. And these quantum interactions leave a subtle but detectable imprint on the properties of the cosmic rays that we observe here on Earth. The analysis of the arrival directions of the highest energy cosmic rays, for example, has revealed a slight anisotropy, a preference for certain directions in the sky, which can only be explained by the deflection of the particles by the weak, but large-scale intergalactic magnetic fields. By modeling these interactions, and by combining the cosmic ray data with observations of high-energy neutrinos and gamma rays, we can begin to piece together a multi-messenger picture of the high-energy universe. A picture where the quantum interactions of these cosmic messengers are a key part of the story. The detection of high-energy neutrinos that are spatially correlated with potential cosmic ray sources. Like the Blazar TXS 0506+056 has been a major breakthrough in this field. Neutrinos, because they are so weakly interacting, can travel in a straight line from their source to us, acting as a perfect, undeflected pointer. The combination of the neutrino signal with the cosmic ray and gamma ray signal from the same source allows us to build a much more complete and robust picture of the underlying astrophysical engine and the quantum properties of the neutrinos themselves. Their ability to oscillate from one flavor to another as they travel is a crucial part of this picture. By studying the flavor ratio of the neutrinos that arrive at Earth, we can learn about the distance to their source and the properties of the medium they have traveled through. The composition of the cosmic rays themselves also holds important clues about their quantum origins. By studying the air showers, the vast cascades of secondary particles that are produced when a high-energy cosmic ray hits the Earth's atmosphere, we can infer the mass and energy of the primary particle. And the data from these experiments suggests that the highest energy cosmic rays are not just protons, but are a mix of heavier atomic nuclei. The study of the interactions of these heavy nuclei at very high energies in experiments at the Large Hadron Collider is providing crucial new data that can be used to model the air showers and to better understand the physics of these cosmic ray interactions. This is a beautiful example of the synergy between accelerator physics and astrophysics, between the study of the very small and the very large. The study of ultra-high-energy cosmic rays is also a powerful probe of fundamental physics itself. These particles have energies that are millions of times higher than anything we can produce in our terrestrial accelerators, making them a unique window into the behavior of matter and the laws of physics at the very highest energy scales. They can be used to test the limits of Einstein's special theory of relativity, to search for tiny energy-dependent variations in the speed of light that are predicted by some theories of quantum gravity. They can be used to search for the signs of new, exotic particles or interactions, for the decay products of super-heavy dark matter, or for the signatures of topological defects like cosmic strings. The study of these cosmic messengers is a journey to the very frontier of our knowledge. A journey that is revealing a universe that is not just full of spectacular, high-energy events, but is also governed by the subtle, beautiful, and deeply quantum rules of the subatomic world. The quantum world, it seems, is not just a strange and distant realm of subatomic particles. It is the very foundation of our cosmic home. Its principles and its paradoxes writ large on the canvas of the cosmos. The journey to understand the universe is, in the end, a journey to understand its deep, and often hidden, quantum nature. The groundbreaking observation of entanglement between top quarks at the LHC is a powerful testament to this. It shows us that the strange, non-local connections of the quantum world are not just a feature of light, low-energy systems, but are a robust and fundamental aspect of reality, present even in the most massive and fleeting of particles, in the most violent and chaotic of environments. This discovery is more than just a confirmation of quantum mechanics in a new regime. It is a new tool, a new window into the quantum heart of the Standard Model. By studying the entangled states of these heavy particles, we are gaining a new and more profound understanding of the Higgs field, of the nature of mass, and of the subtle asymmetries that distinguish matter from antimatter. The study of the exotic quantum states of matter in the hearts of neutron stars is another equally powerful frontier. The observation of phenomena like superfluidity and color superconductivity in these extreme astrophysical laboratories is not just a confirmation of our theories of nuclear and particle physics. It is a glimpse into a whole new realm of emergent, collective quantum behavior. A realm where the familiar rules of our terrestrial world no longer apply. These quantum stars are not just dead, collapsed objects. They are dynamic, vibrant, and deeply quantum systems whose behavior is teaching us new and profound lessons about the nature of matter itself. And the quest to understand the universe's own quantum origins through the study of the cosmic microwave background, of primordial gravitational waves, and of the physics of inflation is perhaps the grandest of all these endeavors. It is a quest that is taking us back to the very first moments of creation, to a time when the entire universe was a single, hot, dense, and deeply quantum entity. The discovery that the vast cosmic structures we see today are the macroscopic fossils of microscopic quantum fluctuations is one of the most profound and beautiful insights in the history of science. It tells us that we are, in the most literal and profound sense, children of the quantum void. The journey to understand the quantum cosmos is a journey that is full of both immense challenges and breathtaking possibilities. It is a journey that is forcing us to abandon our classical intuitions, to embrace paradox, and to develop new and more powerful ways of thinking about the world. But it is a journey that is also, in its own strange way, deeply reassuring. It is revealing a universe that is not a collection of separate, disconnected parts, but a single, vast, and deeply interconnected quantum whole. A universe where the fate of a single particle can be instantaneously linked to another across the galaxy, where the quantum jiggle of the vacuum can seed the formation of 1 trillion stars, where the microscopic rules of the subatomic world can shape the ultimate destiny of the entire cosmos. And as we continue on this journey, as we peer deeper into the quantum heart of reality, we are not just unraveling the secrets of the universe, we are also, in a very real sense, discovering our own deep and undeniable connection to the strange, beautiful, and wonderfully quantum cosmos that has given us birth. It's a night unlike any other, a vast, unbroken expanse of darkness, interrupted only by the cold, distant glow of ancient stars. The blackness of space stretches in all directions, infinite and unyielding. Here, in this silent abyss, time itself seems to lose its meaning. You are an astronaut, floating freely, untethered from your spacecraft. The Earth, a brilliant, swirling marble of blue and white, spins silently below you, a familiar and comforting sight in the overwhelming emptiness. Yet something feels off. A subtle, almost imperceptible wrongness. You glance at your wristwatch, a habit from a world of schedules and deadlines, expecting to see the familiar, steady tick of seconds marching forward. But the hands seem sluggish, reluctant to move, as if they are pushing through an invisible, viscous medium. You blink, shake your head, and look again. Nothing has changed. The hands are still crawling at a snail's pace. Then, a flicker of movement catches your eye in the periphery. The distant stars, which should be constant, unwavering points of light, appear to twinkle at irregular, unsettling intervals. Their light seems stretched, distorted, as if reality itself is bending and warping around you. On board the spacecraft, just a few meters away, your crewmates continue their routine, their voices a faint, tinny murmur in your earpiece. You can see them through the viewport, checking instruments, conversing, floating effortlessly in the familiar embrace of microgravity. Their movements appear normal, their time flowing at the expected, predictable rate. But out here, where you drift alone in the void, time is different. You take a deep, ragged breath, the sound of it loud and alien in the silence of your helmet, trying to calm the rising sense of unease. You have studied this phenomenon before, in textbooks and simulations. Time dilation, a strange and wonderful prediction of Einstein's theories of relativity. But now, experiencing it firsthand, you feel something deeper, something more unsettling than any equation could ever convey. A question, ancient and profound. Echoes in the silent chambers of your mind, what is time? From the moment we are born, we live under the inexorable rule of time. It is the invisible, and often tyrannical, metronome that dictates the rhythm of our lives. It marks the passage of our existence, from the fleeting innocence of childhood, through the striving and struggles of adulthood, to the quiet reflections of old age. It determines when we wake, when we work, when we eat, when we rest. We measure it with our clocks, we count it in our calendars, and we often fear its relentless, unidirectional march forward. But what if this most fundamental aspect of our reality, this thing that seems to govern our every moment, is not as real as it seems? What if everything we experience, the past, the present, the future, is not a flowing sequence of events, but exists simultaneously, a vast, frozen landscape of now? What if time does not flow at all? To us, time feels like a river, a current that carries us inexorably from the fixed, immutable shores of the past towards the unknown, open waters of the future. But some of the greatest and most courageous minds in human history have dared to question whether this powerful, intuitive perception is a true reflection of reality, or is merely an elaborate and deeply convincing illusion created by the workings of our own consciousness. If we could somehow step outside of the universe, if we could adopt a God's eye view and look at time from a higher, inaccessible dimension, what would we see? Would we see a linear, unfolding story, a film playing out from beginning to end, or would we see the entire film at once, every single frame, the first and the last existing simultaneously in a single, timeless, four-dimensional block? The implications of this are profound and deeply unsettling. If time is an illusion, if the future is as real and as fixed as the past, then our cherished and deeply held belief in our own free will may also be an illusion. Every decision we make, every action we take, every single creative thought we have might already be determined, already written into the unchanging script of the cosmos, like a film reel where the ending is already printed on the celluloid. But we, as characters in the story, can only watch it unfold, moment by agonizing, beautiful, and seemingly spontaneous moment. The nature of time has been a battleground for philosophers and scientists for millennia. The ancient Greek philosopher Parmenides, in the 5th century BC, argued that change itself was an illusion. For him, all of reality was a single, static, and unchanging whole. A perfect and eternal sphere of being. Our perception of a flowing, changing world was merely a trick of our unreliable senses, a fleeting and deceptive shadow play on the walls of our mental cave. To Parmenides, the past, the present, and the future already existed, fixed and immutable, and what we experience as the now was just our limited, and ultimately illusory, perspective on this eternal, timeless reality. His ideas stood in stark and dramatic contrast to those of his contemporary, Heraclitus, who believed that change, or flux, was the fundamental and only nature of existence. "No man ever steps in the same river twice," he famously said, "for it's not the same river, and he's not the same man." For Heraclitus, time was not an illusion to be seen through. It was the very essence of reality, the creative and often destructive fire that was constantly shaping and reshaping the universe in an endless, dynamic process of becoming. These two, diametrically opposed ideas, time as illusion versus time as reality, set the stage for thousands of years of intellectual and philosophical debate. Plato, in the shadow of Parmenides, saw time as a moving image of eternity, a mere imperfect reflection of a deeper, timeless, and more real realm of perfect, unchanging forms. His student, Aristotle, took a more practical and in many ways more modern view. He disagreed with the idea of time as an independent, existing entity, arguing instead that it was simply a measure of change. For Aristotle, time was real, but only in relation to the motion and the unfolding of events in the physical world. It had no existence of its own, beyond its role as a way of quantifying the universe's dynamic processes. For centuries, the debate continued, but the dominant view, the one that would come to shape the scientific revolution, was that of time as an absolute, independent entity. When Isaac Newton formulated his revolutionary laws of motion and gravity in the 17th century, he imagined time as a universal, cosmic clock, ticking away at a constant, unvarying rate for all observers, everywhere in the universe, completely independent of the space and the matter that it contained. For Newton, time was like an invisible and infinitely long thread stretching across all of existence, providing a fixed and absolute backdrop against which all the events of the cosmos could be unambiguously ordered and measured. But then, in the early years of the 20th century, everything changed. A young, and at the time unknown, patent clerk in Bern, Switzerland, named Albert Einstein, completely shattered Newton's elegant, but ultimately incorrect, vision of time, with his special, and later his general, theory of relativity. Einstein showed that time was not an absolute, independent, and universal force. It was fluid, it was flexible, it was elastic, and most profoundly, it was deeply and inextricably connected to space itself. Space and time. Einstein argued, were not separate entities, but were two aspects of the same, underlying reality, a single, four-dimensional fabric that he called space-time. The consequences of this idea were staggering, and they have been confirmed by a century of precise and rigorous experimentation. Relativity tells us that time can be stretched and contracted, that its passage is relative to the motion and the gravitational environment of the observer. The faster you move through space, the slower time passes for you relative to a stationary observer. The stronger the gravitational field you are in, the more time slows down. Bending under the immense weight of the universe's most massive objects, time was no longer a universal, cosmic constant. It was a local, personal, and dynamic phenomenon, changing its rhythm and its flow, depending on where you were and how you were moving. This was not just a theoretical speculation. Atomic clocks, the most precise timekeeping devices ever created by human hands, when placed on fast-moving jets or on high-altitude GPS satellites, have been shown to tick at slightly but measurably different speeds compared to their identical counterparts left behind on the surface of the Earth. The implications were profound. If time could be stretched and warped, if its passage was not the same for everyone, then what did that mean for our everyday, common-sense experience of reality? Could time, as we understand it, as we feel it, even be real? Perhaps the most radical and most mind-bending implication of Einstein's unified space-time was the idea of the block universe. If space and time are truly woven together into a single, four-dimensional fabric, then this fabric must contain all of time, just as it contains all of space. The universe is not a film reel that is playing out from beginning to end. It is a completed film, a single, static block of space-time, with every single frame, every moment in history, from the first flicker of the Big Bang to the final, dying embers of the last stars already in place. In this view, the past is not gone, and the future is not something that has yet to arrive. All moments, past, present, and future, exist equally, simultaneously, like different and equally real locations on a vast, four-dimensional map. What we perceive as the flow of time, the feeling of the now moving forward, is merely the path of our own consciousness, the subjective journey of our awareness as it moves along its fixed, predetermined world line through this unchanging, four-dimensional structure. If the block universe model is a correct description of reality, then the future already exists, just as surely and as concretely as the past does. The moment of your birth, the moment you are experiencing right now as you listen to these words, and the moment of your death are all equally real, all frozen into the eternal, crystalline structure of space-time. This is an idea that is deeply and profoundly difficult for the human mind to grasp because it contradicts our most basic and powerful intuitions. We feel time moving forward. We feel it slipping through our fingers like sand. We experience the past as a fixed and unchangeable memory, and the future as an open and unwritten book. But all of this, in the block universe view, may be nothing more than a powerful and deeply convincing illusion, a trick of our perception, a story that our consciousness tells itself to make sense of a reality that is far stranger and more static than our senses can comprehend. And if this is true, it raises a host of deep and deeply unsettling questions about the nature of our own free will. If the future is already written, if every event is already laid out in the four-dimensional map of space-time, then are we truly making choices? Or are we simply actors in a grand cosmic play, following a predetermined script, believing ourselves to be in control, when in reality, every action we take, every thought we have, every choice we seem to make is already fixed, already embedded in the unchanging structure of space-time? Some scientists and philosophers argue that this is the only logical conclusion. If time is truly just another dimension, like space, then the idea of changing the future is as nonsensical as trying to change a particular coordinate in space. The future does not unfold, it simply is, but not everyone agrees with this stark and somewhat bleak interpretation. Some physicists argue that the block universe picture, which is rooted in the classical deterministic world of general relativity, is not the whole story. They argue that time is not a fundamental aspect of reality, but is an emergent property, something that arises from the deeper, more fundamental, and more mysterious laws of quantum physics in the strange and counterintuitive world of quantum mechanics. Time behaves in bizarre and unpredictable ways. Particles can exist in a superposition of multiple states at once, their futures seemingly undecided until the very moment they are measured. Some interpretations of quantum mechanics suggest that reality itself does not have a single, fixed timeline, but instead branches into a vast and constantly growing tree of possibilities. This has led to the concept of the growing block universe, a kind of middle ground between the eternalism of the block universe and the presentism of our everyday experience. In this view, the past and the present are real. They exist. But the future does not. Not yet. The universe is constantly growing, constantly expanding, with new moments, new slices of time, being added as reality unfolds. The future is not predetermined. It is being actively and dynamically created, moment by moment. Its path shaped by the inherent, irreducible uncertainty of the quantum world, and perhaps by the choices of conscious living beings. This concept of a growing, open-ended universe aligns much more closely with our own subjective experience of time. We feel the past as something that is fixed, something that we can remember but cannot change. The future, however, feels uncertain, open, a realm of possibility that we can anticipate, but do not yet see. The growing block universe model suggests that this feeling is not an illusion, but is a true reflection of the nature of reality. The present moment becomes a special and physically real frontier, the very edge of existence, the place where the quantum probabilities of the future are collapsing into the classical certainties of the past. It is the place where reality is being forged. And yet, even this more intuitive idea raises more questions than it answers. If time is truly something that is being created, then what is the mechanism of this creation? What determines how, and at what rate, it unfolds? If the future is not fixed, then what guides the path it takes? And if quantum mechanics allows for a multitude of different possible futures, does that mean that there are multiple parallel realities, alternate timelines that are constantly branching out from our own with every quantum event, with every choice we make? Some scientists and philosophers believe that the ultimate answer to these profound questions may lie not in the external world of physics, but in the internal world of consciousness itself. Our perception of time is so deeply and intimately tied to the way our minds process information, to the very structure of our own conscious awareness. We experience life as a linear sequence of moments, one following another, and this creates the powerful and compelling illusion of a flowing, moving present. But this experience may not be a true reflection of the fundamental nature of time. It may be a feature of our consciousness, a useful and adaptive mental model, rather than a fundamental property of the universe. In this view, our consciousness does not move through time. It simply exists, sequentially, at different points along a pre-existing timeline. In the same way that we only experience one specific location at a time as we move through space, we only experience one single moment at a time as we seem to move through space-time. But all of those other moments, the past, the present, and the future, are equally real, all just waiting in their own specific coordinate in the block universe, to be observed, to be experienced, to be illuminated by the moving flashlight of our own conscious awareness. This is an idea that is incredibly difficult for the human mind to grasp, because it contradicts everything we feel, everything we intuitively know about the nature of time. But if the great scientific revolutions of relativity and quantum mechanics have taught us anything, it is that the universe is far stranger, far more mysterious, and far more beautiful than we could have ever imagined. the familiar, comforting, and seemingly relentless flow of time may be nothing more than an elaborate trick of our own perception, a mental construct that our brains have evolved to make sense of a reality that is far more complex, more static, and more wonderfully timeless than our senses can ever directly comprehend. As you continue to float in the deep, silent void of space, as you watch the Earth slowly, majestically, turn below you, you begin to wonder, is this moment happening now, or has it already happened, 1,000,000 years ago? In the mind of a distant, alien observer, could the future already be written, a story waiting for you to reach its final page? Or is it still being created, its narrative shaped by choices you have yet to make? Perhaps time is not something we move through. Perhaps it is not something that exists at all, in the way we think it does. Perhaps time is simply the way we, as conscious living beings, experience a universe that is already and forever complete, a vast, silent, and eternal tapestry, with every moment laid out, like the infinite, shining threads of a cosmic poem, waiting, unchanging, and beautiful. The idea that our universe is a vast, four-dimensional block of space-time, a static and unchanging reality where all of time exists simultaneously, is a profound and deeply unsettling one. But if it is correct, it raises a tantalizing and inevitable question: if time is just another dimension, like space, can we move freely through it? Can we, in principle, build a machine that could carry us back to the past, to witness the rise of ancient empires, or to meet our own ancestors? Or could we leap forward into the distant future, to see the fate of our species and the ultimate destiny of our world? Science, in its rigorous and often counterintuitive way, suggests that one of these journeys is not just possible, but is a proven and observable fact of our reality. In 1971, in a simple but brilliant experiment, the physicists Joseph Haffel and Richard Keating took a set of highly precise cesium beam atomic clocks and placed them on commercial airliners, flying them around the world, first eastward and then westward. When they returned and compared these airborne clocks to identical, synchronized clocks that had remained stationary on the ground at the U.S. Naval Observatory, they found something astonishing. The clocks that had traveled on the moving planes had ticked at a slightly, but measurably, different rate than the clocks that had stayed behind. Time itself had passed differently for the travelers. This was a direct and stunning confirmation of the time dilation predicted by Einstein's theories of relativity. The faster you move through space, the slower time flows for you, relative to a stationary observer. This means that if a person were to embark on a journey in a spaceship traveling at a significant fraction of the speed of light, they could experience time at a dramatically slower rate than the people they left behind on Earth. A crew of astronauts could travel to a nearby star system and back, a journey that might feel like just a few years to them, only to return to an Earth where centuries or even millennia have passed. In a very real and physical sense, they would have traveled into the future. This is not just a theoretical possibility, it is a constant and necessary consideration in our modern technological world. The high-energy particles called muons, which are created when cosmic rays from space slam into the Earth's upper atmosphere, are a beautiful everyday example of this. These muons have an incredibly short lifespan. They should decay in just a few millionths of a second, and should never have enough time to survive the long journey from the upper atmosphere to the ground. And yet, we detect them here, on the surface of the Earth, in large numbers. The reason is that because they are traveling at very nearly the speed of light, time, from their perspective, slows down dramatically. Their internal biological clocks tick much more slowly than ours, and they live long enough, from our point of view, to complete their journey. Every single astronaut who has ever lived and worked on the International Space Station is, in a small but real way, a time traveler. Their bodies aging just a tiny fraction of a second slower than the rest of us on Earth. Time travel to the future is not just possible, it is a constant and well-verified feature of our relativistic universe. But while the journey forward in time is allowed by the known laws of physics, the journey backward is a far more problematic and far more philosophically fraught proposition. If time travel to the past were possible, it would seem to open up a Pandora's box of logical paradoxes, contradictions that threaten to unravel the very fabric of causality. The most famous of these is the grandfather paradox. Imagine you build a time machine, travel back to the year your grandfather was a young, unmarried man, and for some strange and malevolent reason, you prevent him from ever meeting your grandmother. As a result, your parent is never born, and therefore you are never born. But if you were never born, how could you have possibly traveled back in time to commit the act in the first place? The very success of your mission seems to erase the possibility of you ever having embarked on it. It is a perfect and seemingly inescapable logical loop. And the paradoxes do not stop there. There is the bootstrap paradox, or a causal loop, where an object or a piece of information seems to have no origin. Imagine you are a struggling playwright. A mysterious time traveler appears and gives you a copy of the complete works of William Shakespeare. You then spend your life publishing these plays under your own name, becoming the most famous playwright in history. Then, in your old age, you build a time machine, travel back in time, and give the same volume of plays to your younger, struggling self. The question is, who wrote the plays? They seem to exist in an eternal, self-creating loop, without ever having been written. These paradoxes suggest that there is something deeply, and perhaps fundamentally, wrong with the idea of backward time travel. Physicists and philosophers have proposed several ingenious ways that the universe might conspire to avoid these contradictions. One idea is the Novikov self-consistency principle, proposed by the Russian physicist Igor Dmitrievich Novikov in the 1980s. This principle states that the laws of physics are such that any event that would lead to a paradox simply cannot happen. The probability of such an event occurring is zero. If you were to travel back in time and try to change history, the universe would subtly and inexorably prevent you from doing so. Your gun would jam, your car would break down, you would have a sudden, inexplicable change of heart. Your actions would be constrained in such a way that they always and inevitably lead to the very history that you were a part of. In this view, you can travel to the past, but you cannot change it. You can become a part of the past, but you cannot alter its course. Your presence was, in a sense, already factored in. Another, and perhaps even more radical, possibility is that the universe avoids paradoxes by splitting into multiple parallel timelines. This is the many worlds interpretation of quantum mechanics, applied to the problem of time travel. In this view, every quantum event, every choice, every possibility, causes the universe to branch into a new, parallel reality. If this is the case, then traveling to the past would not take you back into the history of your own original timeline. It would take you to a new and slightly different branch of the multiverse. In this alternate reality, you would be free to act as you please. You could, in principle, prevent your grandparents from meeting, but this would have no effect on your own original timeline. You would simply have created a new parallel universe where you were never born, while your own original universe continues on, unchanged. This is an idea that is often explored in science fiction, the idea of creating alternate histories. It neatly resolves the paradoxes, but it does so at a high price. It means that true time travel, in the sense of returning to your own personal past and changing it, might still be impossible. And it means that any time traveler would be forever marooned in an alternate reality, an orphan of time, forever cut off from the world they came from. But even if the universe has a way of dealing with the paradoxes, there is still the immense and perhaps insurmountable practical challenge of actually building a time machine. The laws of physics, as we currently understand them, do allow for the theoretical possibility of closed time-like curves, which are paths through spacetime that loop back on themselves, allowing an object to return to its own past. In 1949, the great logician and mathematician Kurt Gödel, a close friend of Einstein's, discovered a strange and disturbing solution to Einstein's equations of general relativity. He found that in a universe that was rotating, it would be possible for an object to follow a specific trajectory and to arrive back at a point in its own past. But our own universe, as far as we can tell from our observations, does not appear to be rotating in the way that Gödel's model requires, another and more famous possibility is the wormhole. A wormhole is a theoretical and highly speculative tunnel or shortcut through spacetime, connecting two distant points. First predicted as a possibility by the physicist Ludwig Flamm in 1916, and later explored in more depth by Einstein and his colleague Nathan Rosen. A wormhole is a kind of bridge through the fabric of reality. If a traversable wormhole could be created and stabilized, perhaps by using some form of exotic negative energy matter, it could, in theory, be turned into a time machine. The idea, most famously explored by the physicist Kip Thorne, is that you could take one mouth of the wormhole and accelerate it to very nearly the speed of light, while keeping the other mouth stationary. Due to the effects of relativistic time dilation, time would pass much more slowly for the moving mouth. If a traveler were to then enter the stationary mouth, they could emerge from the moving mouth at an earlier point in time. The two ends of the wormhole would be connected to different moments in time, creating a gateway to the past. But even if this were theoretically possible, the challenges are immense. The amount of exotic, negative energy required to stabilize a wormhole would be astronomical. And any attempt to send something through it could trigger violent instabilities that would cause the wormhole to collapse in an instant. And even if we could overcome all of these immense theoretical and practical challenges, there is still one final and deeply puzzling question. If time travel to the past is possible, then where are all the time travelers? If future civilizations have developed the technology to visit their own past, why haven't we been inundated with tourists from the future? This is a version of the famous Fermi paradox. And it is a question that has no easy answer. Some have argued that perhaps time machines can only travel back to the point at which they were first invented, meaning that no one from the future could ever visit a time before the creation of the first working time machine. Others have suggested that time travelers might be here, but are operating under a strict prime directive of non-interference, carefully observing our history without ever revealing themselves. Or perhaps, and this is a more sobering thought, time travel is just too difficult, too dangerous, or too energetically expensive to ever be a practical reality. And then there is the possibility that there is a deeper, more fundamental law of the universe that we do not yet understand, a law that explicitly forbids backward time travel. The second law of thermodynamics, the inexorable increase of entropy, is a candidate for such a law. If the arrow of time is fundamentally tied to the direction of increasing disorder, then to reverse the flow of time might require the reversal of entropy itself, a process that has never been observed in nature, and which may be fundamentally impossible. A shattered glass on the floor will never spontaneously reassemble itself. The universe seems to have a built-in preference for disorder, for decay, for a one-way journey into the future. Perhaps time, as we experience it, is simply a consequence of this fundamental thermodynamic asymmetry. And if this is the case, then traveling backward in time might not just be difficult. It might be as fundamentally impossible as trying to unbreak an egg. And yet, the question, the dream, the possibility remains. If time is truly just another dimension, like space, then why can we only move through it in one direction? Why can we remember the past, but not the future? If the block universe is real, and all of a sudden moments exist equally, then what is so special about the now? Some physicists and philosophers have suggested that the ultimate answer may lie not in the external world of physics, but in the internal world of consciousness itself. Perhaps our brains are wired in such a way that they can only process information sequentially, giving us the powerful, and perhaps illusory, sensation of a flowing, moving present. In this view, time does not move. We do. Or rather, our consciousness does. As you continue to float in the deep, silent void of space, as you watch the beautiful blue and white earth slowly, ceaselessly, turn below you, the answers seem to be just beyond your grasp. The universe holds its secrets close, waiting for a future generation, a new Einstein, to come along and unlock them. Perhaps one day we will master the mysteries of time, and we will discover whether it is a force we can control, a prison we can escape, or merely a beautiful and deeply human illusion that we can never truly transcend. The very fabric of the universe, the four-dimensional space-time of Einstein's relativity, is not a static, passive stage. It is a dynamic, physical entity that can be bent, warped, and twisted by the presence of mass and energy. And in the most extreme and violent corners of the cosmos, near the event horizons of black holes or in the fiery crucible of the Big Bang, this fabric can be stretched and distorted to its absolute limits. It is in these extreme environments that the true, and often bizarre, nature of time is revealed. The fact that gravity can affect the flow of time, a phenomenon known as gravitational time dilation, is one of the most profound and well-tested predictions of general relativity. The stronger the gravitational field, the more time is stretched, the slower it flows relative to a region of weaker gravity. A clock at sea level will tick just a tiny fraction of a second slower than an identical clock on top of a mountain, where the Earth's gravitational pull is slightly weaker. This is not a theoretical curiosity. It is a real physical effect that must be accounted for in our most precise technologies. Like the global positioning system, the satellites that make up the GPS network are in a weaker gravitational field than we are on the surface of the Earth, and their onboard atomic clocks therefore run slightly faster than ours. If this relativistic effect were not corrected for, the GPS system would accumulate errors of several kilometers every single day, rendering it completely useless. Gravity, it seems, has a direct and measurable grip on the passage of time. And nowhere is this grip stronger than in the vicinity of a black hole. As you approach the event horizon of a black hole, the curvature of space-time becomes increasingly extreme. To an outside, distant observer, your clock would appear to be slowing down, your movements becoming increasingly sluggish. At the very edge of the event horizon, time, from the outside observer's perspective, would seem to come to a complete and utter standstill. You would appear to be frozen in time for all of eternity, your image smeared across the surface of the black hole like a ghostly afterimage from your own perspective. However, as you cross the event horizon, time would be flowing perfectly normally. You would feel no jolt, no sudden change. You would simply have passed the point of no return, your future now inexorably directed towards the infinitely dense singularity at the black hole's core. This strange and beautiful disconnect between the experience of the infalling observer and the distant observer is a direct consequence of the extreme warping of time near a black hole, and it offers a natural, one-way form of time travel If you could somehow build a spacecraft that could hover just outside the event horizon of a supermassive black hole for what feels like a few hours or a few days, and then return to a region of weaker gravity, you would find that you have traveled far into the future of the rest of the universe. Thousands, or even millions, of years could have passed. In this sense, black holes are natural. One-way time machines, portals to the distant future. But if gravity can slow down time, could it also, in principle, be used to reverse it? Could we somehow manipulate the geometry of space-time in such a way that it loops back on itself, creating a pathway to the past? This is the realm of closed time-like curves, and it is a possibility that is allowed, at least in theory, by the equations of general relativity. The mathematician Kurt Gödel, in 1949, was the first to discover a solution to Einstein's equations that contained these strange, time-looping paths. His solution described a hypothetical, rotating universe, a cosmos where the entire fabric of space-time was spinning. In such a universe, the light cones that define the possible future paths of an object would be tilted by the rotation, and it would be possible for a sufficiently fast-moving spacecraft to follow a trajectory that would eventually lead it back to a point in its own past. But our own universe, as far as we can tell, is not rotating in the way that Gödel's model requires. Another, more famous, theoretical possibility for creating a time machine is the wormhole. A wormhole, or an Einstein-Rosen bridge, is a hypothetical tunnel or shortcut through the fabric of space-time, connecting two distant points. Imagine space-time as a two-dimensional sheet of paper. A wormhole would be like folding the paper over and punching a hole through it, creating a direct path between 2 points that would otherwise be very far apart. If a traversable wormhole could be created and stabilized, it could, in theory, be turned into a time machine. The process, as envisioned by the physicist Kip Thorne, would involve taking one mouth of the wormhole and accelerating it to near light speed, while the other mouth remains stationary. Due to time dilation, the clock at the moving mouth would tick more slowly than the clock at the stationary mouth. An age difference would be created between the two ends of the wormhole. A traveler could then enter the stationary mouth, pass through the wormhole, and emerge from the moving mouth at an earlier point in time, effectively traveling into the past. But the challenges to building such a device are immense, and perhaps insurmountable. A traversable wormhole would require the existence of exotic matter, a hypothetical substance with a negative energy density, to prop it open and to prevent it from collapsing into a singularity. We have never observed such matter, and it may be forbidden by the laws of physics, and even if a wormhole time machine could be built, it would be subject to the same unsettling paradoxes of causality that we have already discussed. The universe, it seems, has a deep and powerful aversion to paradox. But the fact that our best theory of gravity allows for these strange, time-bending possibilities is a profound testament to the deep and mysterious nature of time itself. It suggests that time is not a simple, immutable background, but a dynamic, physical, and ultimately malleable aspect of our reality. The deep and unresolved tension between the classical, deterministic world of general relativity and the probabilistic, uncertain world of quantum mechanics is nowhere more apparent than in our attempts to understand the nature of time. If time is a fundamental aspect of reality, as it appears to be in our macroscopic world, then how do we reconcile this with the strange, and often timeless, nature of the quantum realm? Some physicists have come to believe that time itself may not be fundamental at all. It may be an emergent phenomenon, a macroscopic illusion that arises from a deeper, more fundamental, and ultimately timeless quantum reality. This is a radical and difficult idea to grasp, but it is one that is gaining increasing support from several different lines of inquiry in theoretical physics. One of the strongest hints that time may not be fundamental comes from the problem of time in quantum gravity. When physicists try to combine the equations of general relativity with the principles of quantum mechanics, they often find that the variable for time simply disappears from the final unified equation. This Wheeler-DeWitt equation, as it is known, describes a static, timeless, and unchanging wave function of the universe. This has led some to suggest that at the most fundamental level of reality, there is no time, no change, no becoming. There is only a single, timeless, and eternal now. The flow of time that we experience is, in this view, a kind of illusion, a trick of our own, limited, macroscopic perspective. But how could a timeless reality give rise to an experience that is so defined by time? One possibility is that time emerges from the process of quantum entanglement. As we have seen, entanglement is a deep, non-local connection between quantum particles. Some researchers, like the physicist Don Page and his collaborators, have proposed that the universe as a whole can be divided into smaller subsystems, and that the flow of time that we experience is a result of the increasing entanglement between these subsystems. In this picture, time is a measure of the growing correlation, the increasing informational linkage between different parts of the universe. It is an emergent property of the quantum relationships between things, not a fundamental background in which those things exist. Another related idea comes from the theory of loop quantum gravity. In this framework, space-time is not a smooth, continuous fabric, but is quantized, made up of tiny, discrete, indivisible loops or atoms of space and time. In this picture is not a continuous flow, but a series of discrete, quantum ticks, a staccato rhythm of change. Our perception of a smooth, continuous flow of time would be an illusion, a macroscopic averaging over these tiny quantum jumps. In the same way that the smooth, continuous image on a movie screen is an illusion created by the rapid succession of discrete, individual frames. If time is truly an emergent phenomenon, if it is not a fundamental aspect of reality, but is a byproduct of deeper, more fundamental physical laws, then this would have profound implications for our understanding of the universe. It would mean that the question, what came before the Big Bang, is not just meaningless because before requires time, but because time itself may not have existed in the primordial, pre-Big Bang state of the universe. It would mean that our entire, vast, and ancient cosmos, with its 14-billion-year-long history of evolution, could be an emergent structure that has arisen from a timeless and perhaps eternal quantum reality. This also opens up the possibility that our familiar, one-dimensional, forward-flowing time is not the only kind of time that can exist. If time is an emergent property, then different physical systems, different regions of the universe, or even different bubble universes in a larger multiverse, could, in principle, have different emergent temporal structures. There could be universes with two dimensions of time, or with a time that is cyclical, or with a time that does not have a single, well-defined direction. The possibilities are as vast and as strange as the mathematical landscape of quantum gravity itself. But even if time is an emergent illusion, it is a very powerful and a very persistent one. And the reason for this persistence may lie in the nature of our own consciousness. Our brains are biological machines that have evolved to survive and to make sense of a classical macroscopic world. And to do so, they have developed a powerful and deeply ingrained mental model of a linear, flowing time. We construct a narrative of our lives, a story that connects a remembered past with an anticipated future, and we place ourselves at the moving, present moment center of this story. This is an incredibly useful and probably necessary adaptation for a creature like us, but it may not be a true reflection of the fundamental nature of reality. The universe may not have a story, it may not have a past, a present, and a future. It may just be. And we, with our time-bound consciousness, are like travelers in a vast, timeless landscape, our awareness like a single, moving flashlight beam that illuminates one small patch of the eternal reality at a time, creating the powerful and beautiful illusion of a journey, of a flow, of a becoming. The quest to understand the true nature of time is a quest that is still in its early stages. But it is a quest that is taking us to the very heart of the deepest mysteries of physics, of consciousness, and of existence itself. And as we continue to probe the strange and beautiful logic of the quantum world, we may find that the solid, familiar river of time that we thought we were traveling on is in fact, a far more mysterious, more magical, and more wonderfully timeless ocean than we could have ever imagined. No matter how we choose to define time, whether as a fundamental, physical dimension, as an emergent, thermodynamic property, or as a subjective, psychological illusion, our own, personal experience of it feels undeniably real. We are, it seems, trapped in the amber of the present moment, forever looking back at a past we can remember but cannot change, and forever looking forward to a future that we can anticipate but cannot yet know. But why? Why? If the universe is a vast, four-dimensional block where all of time exists simultaneously, do we experience it as a linear, one-way flow? Why does our consciousness seem to be locked into this relentless, forward-moving march? The way we perceive time is a unique and mysterious aspect of our own human consciousness. Our other senses, our sight, our hearing, our touch provide us with a rich, multidimensional, and largely simultaneous picture of the world around us. But time is different. We do not perceive it all at once. We experience it sequentially, moment by agonizing, beautiful, and fleeting moment. Our minds are built to be memory machines and prediction engines. We are constantly weaving the raw data of the present into a coherent narrative tapestry that connects a remembered past with an anticipated future. This is the very structure of our conscious experience, and the source of this temporal structure, many neuroscientists now believe, lies in the intricate and still largely mysterious workings of our own brains. The brain is not a simple, passive clock that ticks off the objective moments of an external time. It is an active and highly creative constructor of our temporal experience. Different regions of the brain seem to be responsible for different aspects of our sense of time. The hippocampus, which is crucial for the formation of new memories, is what allows us to place events in a chronological order, to build the story of our own past. The prefrontal cortex, the seat of our higher-level executive functions, is what allows us to plan for the future, to simulate different possible outcomes, and to make choices based on those simulations. And the cerebellum, a region at the back of the brain that is involved in fine-tuning our motor movements, also seems to play a crucial role in our internal sense of timing, our ability to perceive the duration of short intervals with a high degree of precision. But perhaps the most fascinating insight from modern neuroscience is the idea that our conscious experience of the present moment is not an instantaneous knife-edge point in time. It is a smeared-out, constructed reality, a small window of time known as the specious present, over which our brain integrates the information from our senses to create the smooth, continuous flow of our conscious experience. This window is thought to be a few seconds long. What we experience as now is not a single, infinitesimal instant, but a short, dynamic interval that contains both the fading echoes of the immediate past and the rising premonitions of the near future. This could be the neurological basis for our powerful illusion of a flowing, moving time. If our brains are constantly stitching together these overlapping temporal windows, then the result would be the seamless, cinematic experience of a continuous, unfolding reality. It would also explain why we perceive motion as a smooth flow, rather than as a series of jerky, discrete snapshots, like an old, flickering film. But if our experience of time is a construct of our brains, what does this mean for the objective, physical nature of time itself? Some physicists and philosophers, taking this idea to its logical conclusion, have argued that if our consciousness is what creates the illusion of a flowing, forward-moving time, then time, as we subjectively perceive it, may not be a fundamental aspect of the universe at all. In this view, the universe does not move through time. It is our minds, our consciousness, that creates the illusion of movement. This is an idea that finds a strange and powerful resonance in the world of quantum mechanics. As we have seen, the quantum world is a world of probability and potential, a world where particles can exist in a superposition of multiple states at once. Some interpretations of quantum mechanics suggest that time, at this fundamental quantum level, may not have a well-defined direction, or may not even exist at all in the classical sense. It may only be at the macroscopic level, at the level of our classical measuring devices and our classical conscious brains, that a definite directional arrow of time emerges. The phenomenon of quantum entanglement, that spooky, non-local connection between particles, is a powerful hint that the universe may be more holistic and less sequential than our classical intuition would lead us to believe. If two entangled particles can share information instantaneously, regardless of the distance between them, then this seems to challenge our very notion of a time that is defined by the local, light-speed limited transmission of information. Some have even gone so far as to suggest that time itself may be an emergent property of entanglement. In this radical and highly speculative picture, the flow of time is a consequence of the increasing entanglement between different parts of the universe. The more things become interconnected, the more complex the network of quantum correlations becomes, the more a definite and directional sense of time emerges. This is a breathtaking idea. It suggests that time is not a pre-existing, absolute background, but is a dynamic and relational property of the universe, a property that is being constantly created by the ongoing quantum interactions between its parts. And this opens the door to an even deeper and more profound question. If our own human experience of time is a product of our specific, biological, and classical brains, could there be other forms of consciousness, other kinds of minds, whether artificial or biological, or something far beyond our current comprehension, that experience time in a completely different way? Our consciousness is bound to the linear, sequential processing of information that is characteristic of our neural architecture. But an artificial intelligence, especially a future quantum AI, might not be so constrained. A quantum computer, with its ability to exist in a vast, superpositional state, could, in theory, process a huge number of different, parallel timelines at once. It might be able to experience the future not as a single, unknown path, but as a rich, probabilistic landscape of possibilities. It might be able to experience the past not as a fixed, linear memory, but as a multi-layered, quantum archive that can be accessed and reinterpreted in new and non-linear ways. Or consider a hypothetical, higher-dimensional being. Just as we, as three-dimensional beings, can perceive a two-dimensional drawing all at once, a being that existed in a higher temporal dimension might be able to perceive our entire four-dimensional block universe, our past, our present, our future, as a single, unified, and timeless whole. For such a being, the concept of a flowing time would be as nonsensical as the idea of a flowing space is to us. These are, of course, speculative fictions, but they are fictions that are grounded in the real and deeply puzzling nature of time as it is revealed by our best scientific theories, and they bring us back full circle to the question of our own human free will. If we live in a deterministic block universe, our feeling of choice is an illusion. If we live in a probabilistic quantum universe, our choices may be real. but they may be driven by the random, unpredictable nature of the quantum world, which does not seem to give us any more control over our own destiny. The relationship between consciousness, time, and free will remains one of the deepest and most intractable mysteries in all of human thought. And the paradoxes do not stop there. The very nature of our memory, our ability to access the past, is a profound puzzle. Why can we remember the past, but not the future? The thermodynamic arrow of time provides a partial answer. The past is a state of lower entropy, and the process of creating a memory is a process that increases the overall entropy of the universe. So, it is thermodynamically easy to remember the past, but hard to remember the future. But this does not feel like a complete explanation. The subjective, qualitative feel of a memory is something that is not captured by the equations of thermodynamics. And the strange, and often unsettling, results from neuroscience, which suggests that our brains may be making decisions before we are consciously aware of them. Add another layer of complexity to the puzzle. Are we the authors of our own thoughts and actions? Or are we just the passive witnesses to a complex and largely unconscious neural computation? The quest to understand the relationship between time and consciousness is a quest that is still in its infancy. But it is a quest that is taking us to the very heart of what it means to be a conscious, living, and time-bound being in a vast, strange, and beautiful universe. And as we continue to explore the mysteries of the cosmos, we may find that the deepest secrets of all are not hidden in the distant stars, but in the silent, mysterious, and endlessly fascinating workings of our own human minds. The deep and mysterious nature of time, with its strange paradoxes and its profound philosophical implications, is not just a subject for theoretical physicists and contemplative philosophers. It is a reality that is woven into the very fabric of our everyday lives, a reality that we are constantly navigating, often without even being aware of it. And in this navigation, we are confronted, again and again, with the fundamental and often unsettling tension between the deterministic and the probabilistic, between the fixed and the fluid, between the fate that is written and the future that is open. The observer effect in quantum mechanics, the strange and beautiful fact that the very act of looking at a particle can change its state, is a powerful and direct challenge to our classical notion of an objective, pre-existing reality. It suggests that the past itself may not be as fixed and as solid as we assume. If the state of a quantum particle is not determined until it is measured, then could the past history of that particle also be, in some sense, indeterminate until it is observed? This is the core idea behind the delayed choice thought experiment, first proposed by John Wheeler. In this experiment, a particle is sent towards a double-slit apparatus, but the decision of whether to measure which slit it goes through or to measure its interference pattern is made after the particle has already passed through the slits. And the bizarre result is that the particle seems to know in advance which measurement will be made, and it behaves accordingly. If we choose to measure its path, it behaves as if it had gone through only one slit. If we choose to measure its interference pattern, it behaves as if it had gone through both. It is as if our choice in the present can reach back in time and influence the particle's past behavior. This phenomenon, which has been experimentally confirmed, is known as retrocausality, and it is one of the most mind-bending and deeply mysterious aspects of the quantum world. It does not mean that we can send a message back in time to change history in a way that would lead to a paradox, but it does suggest that the relationship between the past, the present, and the future is a far more subtle, more holistic, and more deeply entangled one than our classical, linear intuition would ever allow. It hints at a reality where the past is not a fixed, immutable record, but is a fluid, probabilistic landscape, a landscape that only solidifies into a definite history when it is observed, when it is measured, when it is remembered. This strange quantum fluidity of the past is mirrored by the deep and unresolved paradox of information in the future, the black hole information paradox. This paradox, as we have seen, is the stark and seemingly irreconcilable conflict between the prediction of general relativity that information is destroyed when it falls into a black hole, and the prediction of quantum mechanics that information can never be lost. The resolution of this paradox is thought to lie in a deeper, and as yet unknown, theory of quantum gravity. And one of the most promising ideas to emerge from this search is the holographic principle. This principle, as we have discussed, suggests that the entire three-dimensional reality of our universe may be a holographic projection of information that is encoded on a distant two-dimensional surface. If this is true, then time itself may not be a fundamental aspect of reality. It may be an emergent property, a part of the three-dimensional illusion, a secondary effect of a deeper, and perhaps timeless, two-dimensional, informational reality. We may only perceive time because we are, in a sense, trapped inside the hologram, forced to experience the unfolding of this informational projection in a sequential, linear way. If we could somehow step outside of the hologram, if we could access the underlying two-dimensional code directly, we might see the entire history of the universe, its past, its present, its future laid out all at once, a vast, static, and timeless tapestry of pure information. This is a breathtaking and deeply abstract idea, but it is an idea that is grounded in the rigorous mathematics of modern theoretical physics, and it is an idea that has a strange and powerful resonance with our own subjective experience. The human mind itself can be seen as a kind of holographic system. Our consciousness is not located in a single point in the brain. It is a distributed, holistic phenomenon, an emergent property of the complex, interconnected network of billions of neurons. And our experience of time is not a simple, linear reading of an external clock. It is a rich, multi-layered, and deeply personal construction, a story that we are constantly weaving from the threads of memory, of perception, and of anticipation. Could it be that our own conscious experience of a flowing, moving time is a clue, a hint, a subjective reflection of the deep, holographic, and perhaps ultimately timeless nature of the universe itself, and what of our own human place in this strange and beautiful, and perhaps illusory, temporal landscape? If time is not what it seems, if the past is fluid and the future is fixed, or if both are part of a timeless, holographic whole, then what does this mean for our sense of agency, for our feeling of free will? The debate between free will and determinism is an ancient one, and the new physics of the 20th and 21st centuries has not resolved it. It has only made it deeper and more interesting. If we live in a deterministic, block universe, then our feeling of choice is an illusion. But even in this picture, our choices still matter. The version of you that is laid out in the space-time block is the version that is the result of a long and complex process of deliberation, of moral reasoning, of conscious choice. The choices are part of the static landscape, but they are still your choices. The quantum world, with its inherent randomness, seems to offer a way out of this deterministic picture, but it is a solution that comes with its own deep problems. If our choices are ultimately driven by the random, probabilistic nature of quantum fluctuations in our brains, then in what sense are they our choices? Randomness is not the same as freedom. A decision that is the result of a random quantum roll of the dice does not feel any more free than a decision that is the result of a deterministic, classical chain of cause and effect. Perhaps the answer lies in a new, and as yet undeveloped, understanding of the relationship between mind and matter. Perhaps consciousness is not just a passive witness to the quantum world, but is an active participant, a force that can somehow influence the outcome of quantum events, that can steer the probabilities in a way that is neither purely deterministic nor purely random. This is a radical and highly controversial idea, but it is one that is being explored by some of the most courageous and creative thinkers on the frontiers of science and philosophy. It is an idea that suggests that we are not just puppets of either classical determinism or quantum chance, but are genuine, creative agents in the unfolding of reality. And this is a vision of our place in the cosmos that is both deeply empowering and profoundly responsible. As our scientific understanding of time continues to evolve, as we continue to probe the strange and beautiful mysteries of the quantum world and the cosmos, we are not just learning about the universe, we are also learning about ourselves. We are learning that our reality is far more subtle, more complex, and more deeply interconnected than we ever imagined. And we are learning that our own conscious experience, with all its beauty, its fragility, and its deep temporal mystery, may be a crucial, and perhaps even central, part of the grand cosmic story. The question of whether we can ever truly travel through time, whether we can break free from the relentless forward march of the present moment, is a question that has captivated the human imagination for centuries. It is the ultimate dream of escape, of second chances, of a mastery over our own and the universe's destiny. And as we have seen, the laws of physics, as we currently understand them, do not entirely slam the door on this possibility. The journey forward in time is not just a theoretical possibility. It is a proven and well understood consequence of Einstein's theory of relativity. An astronaut in a fast-moving spaceship is a real bona fide time traveler, returning to an Earth that is older than they are. The journey backward in time, however, is a far more problematic and far more speculative proposition. The paradoxes of causality, the immense and perhaps impossible engineering challenges, the potential violation of fundamental physical principles like the second law of thermodynamics, all of these seem to conspire to make the past an unreachable and perhaps forbidden country. And yet, the question lingers. If time is truly just another dimension, like space, why can we only move through it in one direction? Why does the universe have such a strong and seemingly unbreakable arrow of time? The answer may be that we are asking the wrong question. Perhaps time travel is not about building a machine that can carry our physical bodies through a fourth dimension. Perhaps true time travel is a more subtle, more informational, and more deeply conscious phenomenon. The quantum world, with its strange, non-local connections and its fluid, probabilistic nature, may offer a different kind of portal through time. The phenomenon of retrocausality, as seen in the delayed choice quantum eraser experiment, suggests that our choices in the present can have a real and measurable effect on the past. This is not the kind of time travel that would allow you to go back and prevent a historical tragedy, but it is a kind of time travel that suggests that the past is not a fixed, dead, and immutable thing. It is a living, responsive reality. A reality that is in a constant, dynamic dialogue with the present and the future. Our memory itself can be seen as a form of time travel. When we remember a past event, we are not just passively replaying a fixed mental recording. We are actively and creatively reconstructing the past in the present. And in this process of reconstruction, we can change the meaning, the emotional resonance, and the influence of the past on our present lives. This is the basis of many forms of psychotherapy. The idea that by revisiting and reinterpreting the past, we can free ourselves from its grip and open up new possibilities for the future. This is a kind of informational time travel, a journey that is not through physical space, but through the rich and often treacherous landscape of our own personal history. But what of the future? Is it a completely open and unwritten book, or are there ways in which we can get a glimpse of what is to come? The universe, in its strange and beautiful way, may be constantly sending us messages from the future. The phenomenon of quantum entanglement, the instantaneous connection between distant particles, is a hint that the universe may be more holistic and less sequential than we think. Some have even speculated that our own human intuition, the sudden flash of insight, the gut feeling that seems to come from nowhere, may be a form of temporal entanglement, a subtle, unconscious connection to our own future states. This is, of course, a highly speculative idea, but it is one that speaks to a deep and universal human experience. The greatest barrier to our understanding of time and of the possibility of time travel may not be a physical one, but a conceptual one. We are so deeply and powerfully conditioned by our linear, sequential experience of time that it is almost impossible for us to imagine a different kind of reality. But the universe, in its strange quantum heart, may be constantly inviting us to do just that. It may be whispering to us, in the language of paradoxes and probabilities, that the past, the present, and the future are not as separate, not as solid, and not as unchangeable as we believe them to be. The ultimate resolution to the puzzle of time travel may not come from a new, grand theory of physics or from the construction of a fantastic new machine. It may come from a shift in our own consciousness, from a new and more profound understanding of our own temporal nature. Perhaps we are all already time travelers, constantly navigating a multidimensional and deeply mysterious temporal landscape, a landscape where the past is always present, the future is always potential, and the now is the magical, creative point where it all comes together. The universe is vast, it is mysterious, and it is full of unanswered questions, and the nature of time is, perhaps, the greatest of these. But the quest to understand it, the journey to explore its limits, its paradoxes, its possibilities, is one of the most exciting, most profound, and most deeply human adventures of all. And it is a journey that is still in its very early stages. The future of our understanding of time is as open and as full of potential as the future of the universe itself.